Welcome to the Deep Sleep Science Channel. Tonight, we'll drift through a quiet museum of forgotten scientific instruments, tools that once turned sunlight into scorch marks, breath into curves, and invisible bay, forces into delicate motion. As you listen, you can simply let each instrument arrive as a small, gentle idea, how it worked, why it mattered, and what it revealed, back when careful hands and key, patient eyes carried so much of science. The Campbell Stokes Sunshine Recorder is a deceptively simple way of letting the sun write its own record. A solid glass sphere acts like a lens, concentrating sunlight onto a curved paper card held in a metal frame, and when the sun is strong enough clear of cloud and gray, haze, the focused beam, scorches a line into the card. The length and continuity of that burn trace are then read as bright sunshine duration, not merely daylight, giving a physical timeline of when the sun was intense enough to leave its mark. What made it valuable was its ruggedness and the fact that it needed no electricity, only a steady mount and routine attention. Yet that same simplicity carried quirks that later sensors avoid. Burn depth and gaps can depend on moisture, card condition, seasonal sun angle, and how. Observer interprets interruptions during broken cloud. Even so, the instrument's quiet strength was that it produced an archivable artifact cards that could be stored and compared year after year, like a small, scorched diary of bright hours. A Nocturnal, sometimes called a horologium nocturnum, is a handheld nighttime timekeeper that lets the sky act as a quiet clock face. Instead of relying on the sun, it uses the position of a reference star relative to Polaris, often with a pointer arm and a rotating dial marked with months or dates. By aligning the device with the pole star and then sighting a bright reference star in the Little Dipper region, commonly Kochab in many traditional instructions, user can read off an approximate local time from the dial. Different versions were made for different latitudes, and many included carefully laid out scales so the same instrument could be used repeatedly under familiar skies. Its usefulness came with gentle constraints that shaped how it was used in practice. Cloud cover, haze, or light pollution could make the reference star hard to find, and the method depended on the user's ability to align accurately and interpret the star's position without rushing. It was never as precise as later marine timekeeping and navigational methods, but it offered something quietly practical for sailors and travelers, a way to estimate time at night when other references were unavailable. Some nocturnals even incorporated tide information for particular ports, reflecting how these instruments were often tailored to the daily needs of navigation rather than to pure astronomical theory. The Crookes Radiometer is the familiar light mill, sealed inside a glass bulb, with tiny vanes that begin to spin when illuminated. The sight is so immediate that it's often treated as a novelty, yet it grew out of a serious experimental culture where vacuum quality, gas behavior, and surface heating were active questions. Inside the partially evacuated bulb, illumination leads to motion that depends strongly on how the remaining gas and the warmed surfaces interact, transforming light and heat into rotation. What makes it especially memorable is the way it sits between intuition and reality. The spinning is not a clean demonstration of radiation pressure in the way many people assume. Instead, it highlights subtler thermal gas effects, and the device's history includes confusion precisely because the motion feels like it ought to be light-pushing. In that sense, the radiometer is a gentle reminder that instruments can be honest, even when our first explanations are not, revealing mechanisms that only Dink become clear with careful interpretation. The Sprengel mercury pump produces high vacuum through a method that feels almost like choreography. Mercury falls as a train of droplets through a narrow tube, And as those droplets descend, they trap and carry away tiny packets of air from the connected vessel. Over time, the system steadily evacuates the space, and in the 19th century, it achieved very low pressures by the standards of the era, low enough to unlock V. Experiments that needed reliable vacuum rather than a rough approximation. Its decline came from several directions at once: the hazards of mercury, the practical inconvenience of operating and maintaining the system, and the rise of newer, mechanical and high vacuum technologies that were cleaner and easier to control. Yet the Sprengel pump remains an emblem of a moment when how good your vacuum is determined what physics you could do at all gas discharges, early electron studies, and a whole landscape of low-pressure phenomena that were otherwise out of reach. The MC Loud gauge measures very low pressures by doing something calmly counterintuitive. It takes a small sample of gas from a vacuum system and compresses it with crass mercury until it reaches a higher, measurable pressure. With known volume ratios and Boyle's law, the instrument lets you calculate what the original low pressure must have been, using the compressed state as a readable proxy for what was too rarefied to read directly. For a long time, it was a standard companion to vacuum apparatus, valued for turning near-nothingness into a number. But it also carried an important limitation that helped push it aside. It cannot measure condensable vapors reliably, so in systems where water vapor or other condensables dominate, the gauge can underrepresent the true vacuum conditions. As electronic vacuum gauges became safer and more convenient, the MC Loud gauge quietly slipped from routine use, leaving behind a clear lesson about how measurement can be biased by what a device is and is not able to sense. The Fizeau toothed wheel apparatus for measuring the speed of light transforms a nearly ungraspable time interval into a mechanical rhythm. Light is sent through a gap in a rotating toothed wheel toward a distant mirror, and depending on the wheel's rotation rate, the returning light is either transmitted again or blocked by a tooth. By finding the rotation speeds that produce extinction or reappearance, the experiment links a known distance to an inferred travel time. What's easy to forget is how much practical engineering lived inside this idea. The method demanded rotational stability, careful alignment over a long baseline, and disciplined interpretation of the extinction condition because the signal is not a digital timestamp, but a subtle transition between visible and not visible. It belongs to a period when time of flight measurement relied on controlled mechanics and patient observation, long before ultrafast electronics and car photodetectors made nanoseconds feel routine. Rotating mirror methods for measuring the speed of light take another gentle approach. Instead of a toothed interruption, a rapidly spinning mirror converts a tiny travel time into a measurable angular deflection. A beam travels along a known path and returns to the spinning mirror. And because the mirror has turned slightly during that travel, the reflected beam's direction shifts by, amount that can be measured as a displacement at a screen or detector. This is a classic example of instrument design turning one kind of smallness into another that's easier to read. When time is too small to measure directly, you transform it into geometry and angle. A shift, a distance then read that instead. These rotating mirror setups became rare as modern lasers and electronics reshaped optical timing, but their logic remains quietly elegant. Make the T imperceptible become visible by changing its form. The Milne-type seismograph uses a horizontal pendulum design to record ground motion from earthquakes onto a moving surface, often paper or smoked glass, so that a transient shaking becomes a stable trace you can archive. The mechanism translates tiny ground shifts into a line that captures timing, amplitude, and wave character, making earthquakes legible not only as events camber, but as patterns that can be compared across locations. Its importance was amplified by networks. When many stations use comparable instruments, distant events can be detected and correlated. Seismology becomes a science of signals rather than anecdotes. Later, broadband digital seismometers expanded frequency and dynamic range, and mechanical recorders became less central. Still, the Milne lineage marks the transition from a world where friction, damping, and pen mechanics shaped the data to a world where calibration and signal processing do. The Wiechert seismograph is often remembered for its physical presence. Massive mechanical instruments with very heavy inertial masses, sometimes tens to hundreds of tas. Kilograms built to stay steady while the ground moved beneath them. Relative motion between the ground and the large mass is recorded, and damping systems help prevent the instrument from ringing too freely, improving the interpretability of the trace. What makes it quietly awe-filled is the philosophy behind it. If you need a stable reference, you can literally build stability through mass. These instruments became rare not because they were useless, but because they were impractical compared with compact sensors that deliver superior bandwidth with far less H-keen. Maintenance. Even so, they embody a past approach to sensitivity, heavy, deliberate, and rooted in the confidence that carefully managed mechanics could reveal motions too. Small to feel. The atmosphere's torsion balance measures tiny variations in Earth's gravitational field by watching a suspended beam twist a fine torsion wire. Small differences in local gravity gradients create torques that rotate the system by minute amounts. And with careful calibration and procedure, those twists can be turned into inferences about subsurface density variations, structures hidden beneath the ground. For early geophysical prospecting, this kind of sensitivity was powerful, especially in searching for oil and mineral formations where density contrasts matter. Over time, it was eclipsed by newer gravimeters and other geophysical methods, yet its conceptual beauty remains. The instrument is not just sensing gravity, but the subtle spatial changes in gravity, using mechanical delicacy rather than electronic amplification to prowl. Make the planet's hidden structure gently measurable. The heliotrope is a surveying aid that uses the sun as an active component of measurement. A mirror reflects sunlight toward a distant observer, creating a bright point that can be sighted across long distances, which is especially useful in triangulation where ordinary targets are difficult to see against rugged terrain or atmospheric haze. What's striking is how it replaces bulk with brightness. Instead of building large towers or markers, surveyors could build visibility by steering sunlight, extending the reach of line-of-sight networks that mapped land with angular precision. As powered beacons, reflectors, and electronic distance measurement advanced, the heliotrope faded from common use, but it remains a calm demonstration of how optical ingenuity can stand in for heavy infrastructure. The planimeter is a mechanical integrating instrument that measures the area of an irregular shape simply by tracing its outline. As the tracer moves along the boundary, a wheel and linkage mechanism converts motion into a direct area reading, letting engineers and cartographers compute key areas without breaking shapes into triangles or running lengthy calculations. Its historical value is deeper than convenience. It made area something you could obtain from a drawing with minimal computation, and it did so by letting physical motion perform a mathematical integration. With the rise of computer-aided design and digital image analysis, planimeters became less common, yet they remain a vivid example of analog computation quietly transforming geometry into a number through carefully constrained mechanics. The Michelson interferometer became, in practice, a workshop instrument, as much as a famous physics idea. By splitting light into two paths and recombining it, it produces interference fringes that shift when mirrors move, allowing extremely fine displacement. measurement with light serving as a ruler. Observing those fringe shifts turned tiny motions into countable changes, enabling precise optical testing and measurement. Older manual setups often sat in wooden or brass frameworks and depended on environmental calm, stable mechanics, controlled air currents, and patient tay. Fringe observation. Modern versions are widespread and frequently automated, but the earlier instruments reveal a gentler truth about precision. Sometimes accuracy is not only a matter of principle, but of stillness, craftsmanship, and a careful relationship between a human observer and a pattern of light. The Fizeau interferometer is widely used to test optical surfaces and measure flatness by observing interference fringes formed between a reference surface, the surface under test. Those fringes act like contour lines of error, making minute deviations visible as changes in spacing and shape, and turning surface quality into a readable map. In lens and mirror fabrication, this mattered because it linked craftsmanship to measurement feedback in a direct loop. Polish, test, interpret the fringes, then polish pass. Again. Modern systems often use lasers and cameras, but older versions relied on careful viewing and interpretation. The calm power of the instrument is that it makes precision tangible and invisible surface. Imperfection becomes a visible pattern that can guide the hand. The Foucault knife edge test for concave mirrors uses a point light source and a knife edge placed near the mirror's focus. As the knife edge cuts into the returning beam, shadows sweep across the mirror's face, and the pattern of bright and dark regions reveals curvature errors across different temor zones of the surface. It is a remarkably sensitive method that turns tiny deviations into easily seen changes in illumination. What makes it enduring is how it lowers the barrier to precision. Even without complex interferometry, the knife edge test can reveal whether a mirror is smoothly shaped or carries subtle zones that will soften an image. It remains known among telescope makers but less familiar in mainstream contexts, and yet historically it made high-quality optical fabrication more accessible, showing that careful geometry and observation can substitute for expensive machinery. The spherometer, in its classic form, measures the radius of curvature of spherical surfaces like lenses and mirrors, using 3 outer legs and a central bar. Micrometer screw. By measuring how much the center rises or falls relative to the plane of the 3 legs, the instrument turns a small mechanical displacement into a geometric paw. Quantity, connecting micrometer precision to optical design requirements. In mirror making, it also served as a process control tool rather than only a final check. Regular readings during grinding and polishing helped makers track whether they were approaching the desired curvature and adjust stroke patterns and pressure accordingly. This turns the instrument into part of an iterative craft loop: measure, adjust, measure again, long before automated manufacturing made feedback invisible. Inside machines. The armillary sphere is often treated as decoration, yet historically it functioned as a demonstrative astronomical instrument. Its rings represent celestial circles, the equator, the ecliptic, meridians, and by rotating and aligning these components, users could visualize, coordinate transformations and seasonal motion, making the sky's geometry tangible in the hands. Its scientific role faded as mathematical methods and star charts improved, but it remains a quiet reminder that instruments are not only for measurement, they can also be for conceptualization, turning an invisible coordinate system into a physical object that can be manipulated, understood, and taught, especially in eras when the sky's motion had to be internalized through geometry rather than computed on demand. An orrery is a mechanical model of the solar system that shows the relative motions of planets around the Sun through geared rotation. Many were built for education and demonstration, Yet they also served as serious tools for communicating ephemeris ideas and the predictability of craft. Celestial mechanics, at a time when accurate printed tables were not always readily available. What makes an orrery quiet to revealing is the way it chooses what to represent physically. Orbits are simplified, intonations may be fixed, and periods approximated, and those choices show what builders and users considered essential: rhythm, order, and relative motion. In the single turning mechanism, an orrery offers a calm mechanical summary of a cosmic system, an analog way to feel celestial regularity. The heliometer measures small angular separations by splitting an image into two and adjusting their relative position until features align. This method supported precise measurements of the sun's diameter and, in historic contexts, enabled important stellar parallax measurements. Rather than relying on perfect pointing, the instrument creates a controllable double image and turns alignment into an angle. Heliometers became forgotten largely because of their mechanical complexity split optics, micrometer adjustments, and the delicacy required to keep everything stable, especially once photography, electronic detectors, and modern interferometry took over. Yet the heliometer's approach remains gently elegant. It turns measurement into coincidence, letting the observer seek a quiet moment of perfect overlap. Then, read the instrument's geometry. A transit telescope is designed to observe the moment a celestial object crosses a reference line, linking sky motion to time determination and longitude calculations. Observers timed transits against regulated clocks, turning the regular sweep of stars into a standard that could anchor civil timekeeping and coordinate observations across distance. These instruments were once essential to national observatories, surveying, and navigation, because time itself was a measurable commodity rooted in astronomy. As atomic clocks and satellite navigation matured, transit work shifted from practical necessity to historical practice. Still, the transit telescope demonstrates a subtle point. Sometimes an instrument's value is not in what it sees, but in how it synchronizes an observation with a standard that everyone can share. A gold leaf electroscope detects electric charge by the quiet divergence of thin gold leaves that repel when similarly charged. It began as a classic electrostatics demonstrator, but it also became important in early radioactivity studies. Ionization in air could cause charge leakage, and the rate of collapse or discharge could be observed and related to the presence of ionizing radiation. Its forgotten character comes from how thoroughly electronic meters replaced visible electrostatic instruments. Yet its historical significance is clear. It provided sensitivity without amplification, using extremely light foil and careful insulation to make wall-dao. Electrical effects visible. In a single small device, abstract charge becomes motion you can watch, and invisible ionization becomes a slow change you can track. The bolometer detects radiant energy by measuring a tiny temperature rise in an absorbing element, often translating that rise into an electrical resistance change. Early bolometers were key in opening infrared studies, enabling detection of thermal radiation beyond what the human eye can see, and helping extend measurement into regions of the spectrum that were previously inaccessible. They were delicate instruments that demanded careful thermal isolation and calibration discipline, because the signal is small and easily swamped by drafts, conduction paths, or changing ambient temperature. Even where bolometric principles persist in modern specialized contexts, the early bolometer remains a quiet milestone, an instrument that feels. Radiation is heat with enough sensitivity to turn invisible energy into a measurable effect. The Van Slyke manometric blood gas apparatus is a glass and mercury system designed to measure small quantities of gases like oxygen and carbon. dioxide released from blood or solutions. A known sample is treated to liberate dissolved gas, and the apparatus measures gas pressure in a fixed volume, producing quantitative values that became Baldar, crucial for physiology and clinical chemistry. Its complexity shaped its fate. Handling mercury safely, maintaining delicate glassware, and practicing precise volumetric technique demanded time and skill, and automated analyzers eventually made blood gas measurement faster and less fragile. Yet historically, the Van Slyke apparatus was transformative. It turned the chemistry of breathing and acid-base balance into laboratory numbers, helping medicine move from qualitative interpretation to quantified data, understanding of respiration and metabolism. The barograph is a self-recording version of the barometer, designed to quietly document how atmospheric pressure changes over time, without needing constant human attention. Instead of a single reading taken at a moment, it uses stacked aneroid capsules that subtly expand and contract as pressure rises and falls. This movement is amplified through a system of levers and transmitted to a pen, which slowly traces a continuous pressure curve onto paper wrapped around a rotating drum. As the drum turns at a steady rate, hours and days unfold as a smooth line, revealing gradual trends, sudden drops, and gentle oscillations in the atmosphere. What made barographs especially valuable was their ability to preserve patterns rather than isolated numbers. Meteorologists could see the signature of an approaching storm, the calm stabilization after a front passed, or small rhythmic fluctuations that might otherwise go unnoticed. Over time, many barographs fell out of everyday use, not because they stopped working, but because they demanded care. Fresh ink, chart replacement, periodic calibration, and mechanical cleaning to prevent friction or hysteresis from distorting the trace. In return for that care, the instrument offered something quietly rare: a continuous, physical memory of the sky's pressure, written patiently by the air itself. The actinograph is a recording instrument designed to track the intensity of solar radiation over time, translating invisible energy from the sun into a gentle, continuous trace. In many designs, sunlight warms an absorbing surface or element, and that thermal response is converted into motion that drives a pen across a rotating chart. As hours pass, the instrument produces a flowing record of how solar input rises in the morning, peaks near midday, and softens again toward evening, capturing both daily rhythm and the interruptions caused by clouds or haze. Before electronic radiometers and data loggers became common, actinographs played an important role in agriculture, climatology, and atmospheric science. They allowed researchers to study not just how bright the sun was at a given moment, but how solar energy accumulated and fluctuated throughout the day. Their decline came as electronic sensors offered higher precision with less mechanical upkeep. Yet the actinograph remains a calm example of early continuous measurement, where warmth, leverage, and time worked together to let sunlight leave a drawn signature of its passing. The heliometer is an optical instrument created to measure extremely small angular separations by splitting an image into two and allowing their relative K, positioned to be adjusted with great precision. By carefully sliding or rotating optical components until two images of the same object coincide, the observer can determine tiny angles that would otherwise be difficult to measure directly. This technique made the heliometer especially valuable for precise measurements of the sun's diameter and for early stellar parallax work, where minute shifts carry profound meaning. Although conceptually elegant, heliometers were mechanically complex, requiring stable mounts, finely controlled adjustments, and careful observation. As photography, electronic detectors, and modern astrometry advanced, these instruments gradually faded from routine use. Still, their legacy remains gentle and clear. Rather than chasing absolute accuracy, the heliometer turned measurement into a quiet act of alignment, where coincidence itself became the signal and geometry did the rest. The meridian circle is a highly specialized astronomical instrument designed to measure the precise positions of stars as they cross the local meridian. Mounted so it moves primarily in a single plane, the instrument allows observers to record the exact time and angle at which a star passes this reference line. Over repeated observations, this method supported the creation of detailed star catalogues and helped refine measurements of Earth's rotation and orientation. These instruments demanded extraordinary care, stable foundations, temperature control, precise graduated circles, and meticulous correction from tar. Instrumental and atmospheric effects. Meridian circles gradually became less central as photographic methods, electronic detectors, and space-based astrometry took over. Yet historically, they represent one of the purest expressions of positional astronomy, where patience, repetition, and mechanical precision combined to let the sky slowly reveal its coordinates. The transit telescope is closely related to the meridian circle, but is optimized specifically for timing celestial crossings. As stars or planets pass through the telescope's narrow field of view aligned with the meridian, observers record the exact moment of transit against a highly regulated clock. In this way, the regular motion of the heavens became a standard for determining time and longitude, linking astronomy directly to navigation and civil timekeeping. Before atomic clocks and satellite systems existed, transit observations were essential to national observatories and surveying efforts. Their importance lay not in dramatic imagery, but in synchronization connecting distant places through shared time. As modern timekeeping technologies emerged, the transit telescope shifted from practical necessity to historical artifact, quietly marking an era when the sky itself served as humanity's most reliable clock. The armillary sphere is often admired for its beauty, but historically it functioned as a working scientific instrument for understanding celestial geometry. Composed of interlocking rings representing the equator, ecliptic, meridians, and other fundamental circles, it allowed users to physically model the motions of the heavens. By rotating the rings, one could visualize rising and setting, seasonal change, and coordinate transformations in a tangible, spatial way. As astronomy became increasingly mathematical and computational, the armillary sphere's role as a working instrument diminished. Yet its scientific value lies in how it made abstract systems visible and manipulable. Rather than producing numbers, it produced understanding, offering a calm, physical way to grasp how the sky is structured and how motion unfolds across it. The orrery is a mechanical model of the solar system that uses gears to represent the relative motions of planets around the Sun. Turning a handle sets the system in motion, revealing how orbital periods differ and how planets return to familiar configurations over time. Though simplified, orreries embodied the idea that celestial motion is orderly, predictable, and governed by underlying rules that can be represented mechanically. Before widespread access to accurate printed tables and calculations, orreries served as practical, educational, and explanatory tools. Their limitations, fixed inclinations, approximate periods are part of their quiet charm, reflecting what aspects of planetary motion were considered most scarce, important to show. In a single turning mechanism, the vastness of the solar system was gently compressed into something that could be held, watched, and understood at human scale. The sextant is best known as a navigational instrument, but it also played an important scientific role in measuring angular relationships between celestial objects and the horizon. By using mirrors to bring two images into alignment, The sextant allows precise angle measurement without requiring the instrument to be held exactly level. This innovation dramatically improved accuracy at sea and enabled systematic celestial observation under challenging conditions. Over time, satellite navigation reduced reliance on sextants, yet their scientific importance remains. They represent a refinement of angular measurement that balanced optical ingenuity with human ergonomics. The sextant's quiet power lies in its ability to turn alignment, two images touching into reliable knowledge about position, time, and motion. The octant, an earlier cousin of the sextant, measures angles up to 90 degrees using mirrored optics. It was widely used in navigation and astronomical observation before sextants became standard, offering a practical compromise between precision and d'Air. Manufacturability. For many years, it was the instrument that connected sailors to the sky in a repeatable, teachable way. Though eventually replaced by sextants with wider range and improved optics, the octant played a crucial transitional role. It shows how measurement evolves incrementally through improvements in materials, optics, and usability than through sudden replacement. Quietly, it helped standardize celestial navigation during a formative period of global exploration. The theodolite, in its early scientific forms, was not only a surveying tool but a precision instrument for measuring angles in geodesy and astronomy. Combining telescopic sights with finely graduated circles, early theodolites allowed careful measurement of horizontal and vertical angles, supporting efforts to map land accurately and understand Earth's shape. Before electronic distance measurement and satellite positioning, theodolites demanded disciplined technique, careful leveling, repeated readings, temperature, awareness, and correction for instrument error. Their gradual disappearance from everyday practice reflects technological change, yet they remain a calm testament to how much precision can be achieved through mechanical refinement and patient observation alone. The repeating circle was designed to improve angular measurement accuracy by repeating the same angle multiple times and accumulating the result. Instead of relying on a single reading from a fine scale, the instrument effectively averaged out small errors through repetition, allowing greater precision even when engraving resolution was limited. This approach became unnecessary once digital encoders provided direct high-resolution angle measurement. Still, the repeating circle illustrates a gentle philosophy of instrumentation. When perfectioning components is difficult, clever procedure can compensate. The instrument does not fight. It calmly dilutes it through repetition. The planimeter, beyond its practical use, represents an analog approach to mathematics, embodied in metal and motion. By tracing the outline of a shape, the user allows the instrument's internal geometry to perform an integration, converting movement into area. No equations need to be written. The answer appears directly on a scale. As digital tools replaced mechanical computation, planimeters became less common. Yet they remain deeply instructive. They show that complex mathematical operations can be carried out physically, with the instrument quietly doing the work while the user follows a line, unhurried, letting motion become meaning. The harmonograph draws intricate curves created by the combination of multiple harmonic motions, often using pendulums connected to a pen. As the pendulums swing and gradually lose energy, the pen traces looping, evolving patterns that reveal relationships between frequency, phase, and damping. While often admired for their beauty, harmonographs also served educational and scientific purposes, making abstract concepts of superposition, resonance visible. Long before electronic displays, they offered a calm way to see time unfold as form, with physics leaving behind a delicate, slowly settling signature. The torsion balance measures extremely small forces by observing how a suspended fiber twists under applied torque. With careful isolation and calibration, these instruments revealed gravitational, electrical, and magnetic effects far below everyday perception, turning sour. Minute forces into measurable angles. Their sensitivity required patience and stillness, as air currents and temperature changes could overwhelm the signal. Though modern sensors often replace them, torsion balances remain a quiet monument to precision, through delicacy where the smallest motions carry the deepest key: information. The mirror galvanometer detects tiny electric currents by attaching a small mirror to a moving coil or magnet. Instead of moving a heavy needle, the system reflects a beam of light onto a distant scale, amplifying minute deflections into large, readable movements of the light spot. This optical amplification allowed detection of signals too weak for mechanical meters, especially in early telecommunications and laboratory physics. Though electronic amplifiers eventually replaced it, the mirror galvanometer shows how light itself once served as an amplifier, magnifying subtle electrical whispers into visible motion. The ballistic galvanometer is designed not to measure steady current, but the total charge delivered in a brief pulse. Its moving system responds slowly, so a short impulse produces a single swing whose amplitude corresponds to the integrated charge that passed through. This made it invaluable for studying capacitors, electromagnetic induction, and transient phenomena before oscilloscopes existed. It teaches a quiet lesson about measurement. Sometimes what matters is not the instantaneous value, but the accumulated effect, a quantity that can be captured in one graceful movement. The quadrant electrometer measures electric potential differences using electrostatic forces rather than current flow. A lightweight charged element moves within fixed quadrants, and its deflection indicates voltage with remarkable sensitivity for its time. As electronic voltmeters became more convenient, quadrant electrometers faded from use. Yet they remain a gentle example of pre-electronic sensitivity, where careful mechanical design and electrostatic interaction turned invisible potentials into observable motion. The capillary electrometer uses changes in surface tension at a mercury electrolyte interface inside a fine tube to detect voltage. Small potential differences cause the mercury meniscus to shift, converting electrical signals into visible displacement. Though limited in speed and accuracy compared to modern electronics, it played a crucial transitional role in early electrophysiology. It shows how fluid behavior once formed part of the measurement chain, blending electricity, chemistry, and mechanics into a single responsive system. The string galvanometer replaced heavy moving parts with an extremely fine conductive filament suspended in a magnetic field. Tiny currents caused the string to deflect, and optical magnification made the motion recordable, enabling early bioelectric measurements. This instrument laid groundwork for recording physiological signals, including early heart activity studies. Its quiet elegance lies in reduction, less mass, less friction, allowing delicate electrical phenomena to express themselves without being smothered by the instrument. The early electrocardiograph, before becoming a compact device, was a system of instruments working together: electrodes, sensitive galvanometers, timing, references, and recording surfaces. Operating it required careful preparation and environmental control, but the result was transformative, a repeatable record of the heart's electrical rhythm. As technology advanced, these complex systems became simpler and more automated. Yet their historical role is profound. They mark the moment when internal biological processes became visible as curves and intervals, turning living rhythm into something that could be measured, compared, and gently understood. A graphometer, also known historically as a semicircle or semicircumferentor, is an older angle measuring instrument that helped turn surveying into a repeatable geometry practice. It typically consists of a semicircular graduated limb with a pivoted sighting rule called an alidade, allowing a surveyor to sight along a line to a distant point. Read the corresponding angle directly from the scale. In the field, that meant angles could be captured as numbers rather than as rough judgments, supporting triangulation and systematic layout for land boundaries, fortifications, and engineering work. What made the graphometer feel forgotten is that it sits in a lineage that led to more capable full-circle instruments, and eventually the theodolite, which offered Prach, improved mechanics and broader measurement range. Even in its own time, precision depended on very practical details. How finely the limb was engraved, how well the instrument was centered and leveled, often with a plumb bob, and how consistently the surveyor could repeat observations to pite, reduce small errors. In that way, the graphometer wasn't only a piece of metal with a scale. It was a disciplined method in instrument form, asking for steady setup and repeated sighting so an angle could become a trustworthy quantity. The dioptra is a classical surveying and astronomical instrument, often described as a sighting device paired with a graduated circle, and it can be thought of as one of teen, the ancestors of later angle measuring instruments like the theodolite. In traditional descriptions associated with Greek and Roman engineering, a dioptra could include a sighting tube or aligned sights for targeting distant points, with a mechanism for reading angles on a scale. It was used in contexts where controlled angular measurement mattered, such as aligning structures, planning routes, and supporting the geometry needed for large construction projects. Its historical importance is closely tied to early precision infrastructure, especially the engineering challenges of channels and aqueducts. If you want water to flow reliably over long distances, you need not only strength and stone, but accurate direction and carefully managed slope. And the dioptra provided a way to treat angles as something measurable and repeatable rather than guessed. Accounts connected to figures like Hero of Alexandria highlight its role in translating geometric ideas into practical field procedure. Even where surviving physical examples are rare, the dioptra remains a calm reminder that ancient engineering depended on instruments that disciplined, that gave human eye and hand into consistent measurement. The chorobates was an ancient leveling instrument closely associated with Roman engineering, built to establish horizontal lines over distances where small errors could grow into major failures. In descriptions attributed to Vitruvius, it is portrayed as a long, rigid beam supported on legs, designed to be set in position so the builder could judge true prayer. Level. Some versions relied on plumb lines hanging from the ends to indicate vertical alignment, helping the operator ensure the beam was not tilted and that the reference line was steady. What makes the chorobates especially distinctive is its use of water as a leveling reference in calm conditions. A shallow groove along the beam could be filled with water, and the water surface, naturally horizontal, would reveal minute tilts that plumb lines might miss when wind or vibration disturbed them. This combination of geometry and fluid steadiness reflects a practical understanding. When you are building aqueducts and channels across kilometers, the instrument must be able to resist small disturbances, because even slight vertical errors can accumulate into large problems. In that sense, the chorobates is not just a historical curiosity. It's a quiet lesson in how engineering scale forces measurement to become serious. The groma was a Roman surveying tool built for one fundamental task: laying out right angles so roads, plots, and camps could be organized into clear geometry. It typically consisted of a vertical staff with cross arms set at right angles, from which plumb lines were suspended. By aligning the plumb lines with distant markers, a surveyor could establish perpendicular directions with repeatable consistency, creating the straight streets and khanda. rectangular grids that became a recognizable feature of Roman planning. Its effectiveness depended on the calm management of simple physical references, and it carried gentle vulnerabilities. Wind could move plumb lines, uneven ground could complicate stable setup, and sighting was limited by visibility and the care taken in alignment. Over time, as surveying instruments developed finer scales and more versatile sighting and leveling systems, the Groma became less central. Yet it represents an important stage in measurement history, turning an abstract concept perpendicularity into a practical field tool that could impose order on large spaces with quiet, mechanical clarity. The plane table is a field mapping instrument that allows a surveyor to draw a map directly while observing the landscape, blending measurement and documentation into one continuous workflow. Mounted on a tripod, the table is leveled, and a sheet of paper is fixed to its surface. Using an Ali-Dida straightedge with sights, the AR surveyor can sight to a feature and draw a line on the paper in the corresponding direction, gradually building a map by intersection and plotting without needing to record separate angle and distance data for later drafting. This approach was especially useful in topographic work, where immediate visualization helped guide the next observations and where terrain made repeated relocation difficult. The plane table's strengths were also its limits. It depended on good weather, stable paper, and clear lines of sight, and it could be awkward in rain, strong wind, or low visibility. Over time, photogrammetry, total stations, and satellite-based mapping made field drawing far less common. Still, the plane table remains a calm example of an older surveying philosophy. Make the measurement visible as it happens, so the map emerges gently, continuously from the act of looking. A circumferenter is a full-circle surveying compass designed to measure bearings with a 360-degree graduated circle, typically paired with sighting gray, vanes for aligning with distant points. Unlike semicircular angle tools, it provides a complete circular scale around the compass, supporting traverse surveys where a surveyor moves from station to brow. Station and records directional bearings systematically. In many practical contexts, it offered a sturdy and portable way to connect field directions to mapped lines without requiring the more elaborate optics of Tammer. Later instruments. Its limitations are inseparable from the physics of magnetism. Magnetic declination, local magnetic anomalies, and nearby iron objects could bias readings, and careful surveyors had to understand these effects to avoid drifting off true direction over long traverses. As transit instruments and theodolites became more widespread, bringing improved angular precision and reducing magnetic dependence, the circumferentor gradually became less central. Yet it represents a significant period in measurement history when compass-based geometry was a dominant language of land mapping, quietly organizing grass, space through repeated bearings and careful correction. Gunter's chain is a measuring chain standardized for surveying, famously 66 feet long and divided into 100 links, created to make land power. Measurement, arithmetic, more convenient. Its length ties neatly into common land units, making it easier to compute acres and subdivisions without constant fractional conversion. In practice, chain crews could measure distances by laying the chain along the ground in repeated lengths, counting chains and links, and recording results that could be turned into plats and property boundaries with consistent procedure. The chain's practical challenges were as real as its convenience. It could sag, vary with temperature, catch on vegetation, and depend on the steady coordination of the crew. Even small deviations pulled tension. Uneven terrain, worn links could affect accuracy across long lines, which is why standardization and careful technique mattered so much. Over time, steel tapes, invar tapes, and electronic distance measurement reduced reliance on chains. Still, Gunter's chain remains a gentle symbol of a surveying era where distance was measured by coordinated human movement and a physical standard. Link by ewe. Link across the land. The odometer wheel, often called a surveyor's wheel, measures distance by converting the rolling motion of a wheel with known circumference into linear distance, typically displayed through a mechanical counter. As the wheel moves along a path, each rotation represents a fixed length traveled, and the instrument accumulates those rotations into a readout. It offered a practical way to estimate distances along roads, paths, and boundaries without repeatedly laying down a tape or chain, and it could be used quickly over Tamia. Long stretches. Its convenience came with predictable sources of error that careful users learned to respect. Rough terrain, wheel slippage, soft ground, and uneven surfaces can cause the wheel's rotations to diverge from true distance, especially over bumpy or muddy paths. Even wheel wear and the exact way the wheel is held can slightly influence results. Despite these limitations, the odometer wheel became a familiar tool because it made distance feel immediate walk the line. And the instrument quietly counts, showing how measurement sometimes favors practical speed and consistent procedure over laboratory-grade precision. Meridian lines are Neyerman-based astronomical instruments, often built into large public interiors such as churches or observatories, designed to mark AT, solar noon, and track seasonal change with high repeatability. A small aperture, sometimes a carefully placed hole high in a wall, projects an image of the sun onto the floor, where a line marks the local meridian. As the sun's image moves across the interior, the moment it crosses that line gives a precise reference for solar noon, and its position along the line shifts through the year. The sun's declination changes. Historically, these installations supported calendar reform, clock calibration, and long-term observation of solar behavior using architecture itself. As the instrument body, they worked best when the building was stable and the aperture geometry carefully chosen, turning daily sunlight into a reliable moving marker without mechanical demony. Clocks inside the system. As precise timekeeping became portable and independent of solar observation, meridian lines became less central to practical timing. Yet they remain a quiet demonstration of an older scientific strategy. Build a measurement so large, stable, and simple that it can repeat itself for decades, letting the sun return each day to confirm the geometry. Photographic plate measuring engines were built for the era when the sky was recorded on glass plates, and the scientific task shifted from capturing the image, extracting precise numbers from it. These machines typically used a microscope mounted above a movable stage that held the photographic plate, with finely controlled motion in two directions through micrometer screws or precision slides. By centering star images under the microscope crosshairs and reading the stage coordinates against reference scales, operators could produce accurate positional measurements, turning points of light into catalog entries. What made these engines so important is that they formed a distinct second instrument in the data chain. The telescope created the plate, and the measuring engine converted it into quantitative astrometry. This separation mattered because positional accuracy depended not only on optics and exposure, but also on stable mechanical motion, careful referencing, and consistent interpretation of star image centers. As digital detectors and automated astrometric reduction became dominant, plate measurement engines faded from everyday use. But their role remains quietly foundational. They enabled systematic star catalogs and precise comparisons over time, showing how astronomy often depends as much on measurement extraction as on observation itself. The blink comparator is an instrument designed to help the eye detect change by rapidly alternating between two images of the same region of sky taken at trine. different times. By blinking back and forth, any object that moved like an asteroid or changed brightness like a variable star stands out as a shifting or flickering curve. Point against a stable background. The tool essentially trains human vision to do what it does naturally. Notice movement and difference, but with a controlled rhythm that makes subtle changes easier to catch. Its historical power came from simplicity, paired with a deep understanding of perception. Instead of asking an observer to scrutinize two photographs side by side and hold differences in memory, the instrument turns time variation into an immediate visual event. For many decades, this method was central to discovery workflows, where human attention served as the detector and the comparator provided speed and clarity. As digital difference imaging and automated detection became reliable and fast, blink comparators became far less common. Yet they remain a calm reminder that instruments can amplify not only physical signals, but also cognitive strengths, making the human eye part of a deliberate measurement system. Waveform recording on smoked paper or smoked glass was a widely used technique for capturing delicate, fast or low-force signals without burdening the source. A surface would be coated with a thin layer of soot, creating a dark, easily marked background. A stylus connected to the measuring mechanism, whether a physiological transducer or a vibration pickup, would scratch away the soot as the recording surface moved, leaving a sharp, high-contrast trace. This allowed subtle motions to be recorded with minimal friction, which mattered when a heavier ink pen would damp or distort the signal. The method's significance is often hidden in how practical it was for its time. In physiology, engineering, and experimental mechanics, it enabled clear traces of transient events and fine oscillations, producing records that could be preserved, measured, and compared. It also highlighted a key instrumentation lesson. Recording is not neutral. Your recorder can change what you are recording, so smoked paper offered a way to reduce loading on sensitive systems. As electronic sensors and digital acquisition replaced mechanical tracers, smoked paper recording became rare. But it remains a quiet landmark in measurement history, where the simplest materials, soot, glass, a moving drum made fleeting signals stay still long enough to be studied. A pneumograph is an instrument designed to record breathing by tracking the physical motion of the chest or abdomen. Many classic pneumographs use belts, levers, or flexible tubes placed around the body so that expansion and contraction during respiration becomes a measurable movement. That motion can then be written onto a recording surface, often a rotating drum, producing a continuous curve that shows breathing rhythm, depth changes, responses to stimuli over time. Its value in early physiology came from turning an internal process into an external trace, allowing researchers to compare breathing patterns across conditions, individuals, or experimental interventions. At the same time, the pneumograph illustrates the subtlety of measurement. By proxy, chest motion is related to airflow and volume, but not identical to them, and the strength of the inference depends on placement, tightness, and the mechanics of the coupling. Modern respiratory monitoring uses electronic sensors and integrated systems, which makes older pneumographs easy to overlook. Yet their traces help shape how respiration was studied quiet, repeating waves that made breathing visible as data. The Meritamba is a mechanical pressure transducer that converts pressure changes into motion using a flexible membrane connected to a lever and stylus. When pressure rises or falls, whether from breathing, pulse waves, or other physiological pressures, the membrane deflects slightly. The lever amplifies that motion, and the stylus records it as a curve. Used with a chemograph or similar recorder, it allowed pressure phenomena that could not be seen directly to become stable lines that could be measured and compared. Its historical importance lies in how it standardized the conversion from pressure to trace, at a time when electronic transducers did not yet dominate. But it also carried engineering demands that shaped its performance. Low inertia, so it could respond quickly. Appropriate damping, so it would not ring or overshoot bark. And careful setup to avoid introducing artifacts from tubing or mechanical friction. As electronic pressure sensors and digital acquisition systems became widespread, the merry timbre receded from routine use. Still, it remains a calm example of how physiology became quantitative membranes, levers, and moving paper quietly translating the body's pressure rhythms into analyzable form. Riefler precision pendulum clocks were developed as laboratory-grade timekeeping instruments, valued for exceptional stability in observatories and the E. Standards laboratories where time served as a foundation for other measurements. Their design emphasized minimizing friction, stabilizing temperature effects, and delivering a consistent impulse to the pendulum so that its period remained P, as uniform as possible. In such settings, a precision clock was not merely telling time. It was acting as a reference against which astronomical observations were timed, geodetic C. Measurements were coordinated and experimental procedures were synchronized. What made these clocks historically significant is how directly they show time as a measured quantity that required continual care and verification. A stable environment, careful maintenance, and periodic comparison were part of making the instrument function as a standard, rather than as a decorative object. As quartz oscillators and later atomic time standards replaced pendulum systems, Riefler clocks became less central, not because time mattered less, but because better stability became easier to obtain in smaller packages. Yet the Riefler tradition remains a quiet reminder that precision often depends on disciplined control of tiny influences: temperature drift, friction, impulse. Consistency because, over long periods, the smallest errors become the largest. Marine chronometers are often associated with navigation, but they also served as scientific instruments for longitude determination, time transfer, and coordinated surveying. By carrying a stable time reference from one place to another, surveyors and observatories could synchronize observations across distance, making it possible to compare celestial events or establish longitude differences with practical reliability. In an era before radio time signals and global satellite systems, chronometers were among the few ways to transport accurate time, and that portability made large-scale mapping and coordinated science far more achievable. Their use demanded careful ritual, which became part of the instrument's identity. Chronometers had to be protected from shocks and temperature extremes, wound correctly on schedule, and routinely compared against other references to detect drift. In that sense, the chronometer was both a device and a practice. Precision depended on handling as much as on engineering. As radio signals, quartz timing, GPS, and atomic standards transformed time distribution, chronometers became less central. Yet their historical role remains quietly profound. Time was once something you carried, safeguarded, and constantly checked, because measurement across the world depended on that traveling heartbeat. Zenith telescopes are specialized astronomical instruments designed to measure small variations in latitude by observing stars near the zenith, where the line B of sight is almost straight up. By focusing on stars close to overhead, these telescopes reduce certain observational difficulties and help improve precision, because some atmospheric and AT geometric effects are easier to manage near the zenith. In practice, the instrument supported geodetic studies of Earth's shape and subtle motions, treating latitude not as a fixed fact, but as a quantity that can shift slightly due to Earth's complex behavior. Their gradual decline reflects the rise of modern geodesy methods, including space-based measurement and advanced detectors, which can capture Earth. Orientation and position changes with new levels of accuracy and continuity. Still, zenith telescopes represent a distinct historical strategy. Rather than trying to overcome every error source with brute force, they narrowed the observational problem to a favorable region of the sky where careful design could squeeze out more reliability. They remind us that instrument specialization is often a way of negotiating with nature, choosing the geometry that makes measurement gentler, steadier, and more precise. The Horibo-Talcott method uses an instrument and observing strategy designed around paired stars at equal zenith distances north and south. By observing two stars symmetrically placed around the zenith, the method cancels many systematic errors because the geometry is balanced, biases that affect one craft. Observation often affect the paired observation in a compensating way. The instrument setup and the procedure work together, turning symmetry into a tool for accuracy and enabling refined latitude measurement beyond what many single creed star methods could achieve. This approach is historically important because it demonstrates a powerful measurement philosophy. You do not always need a perfect instrument if your method is designed to subtract out imperfections. The paired star technique reduces the influence of certain instrumental offsets and atmospheric effects, making the final result more robust. As modern instruments and space-based systems made latitude measurement easier and more automated, the Horibo-Talcott approach became less common. Yet it remained a calm and instructive example of how clever observation design rooted in symmetry and repetition can turn real-world imperfections into manageable, cancelable terms. The astrolabe is a practical measuring and calculating device that once sat at the intersection of astronomy, navigation, and everyday timekeeping. Using engraved plates and a rotating pointer, it can measure the altitude of celestial objects, help determine the time from the sky, and solve a range of geometric and trigonometric problems through physical rotation and alignment. Instead of requiring the user to compute everything from scratch, the astrolabe embodies relationships between coordinate systems and celestial motion in a form that can be manipulated by hand. Its decline came as specialized instruments, and later electronic navigation and computation made many of its functions easier, faster, and more precise. Yet the astrolabe's historical importance is not only what it measures, but how it thinks. It is an analog problem solver, a compact geometry engine that turns the sky into a readable and workable diagram. It reminds us that instrument can mean more than a sensor. It can be a structured representation of knowledge that lets a user transform observation into answers through calm, repeatable physical steps. The Campbell Stokes Sunshine Recorder is a deceptively simple meteorological instrument meant to measure bright sunshine duration, not the total length of TAD. Daylight. At its heart is a solid glass sphere that acts like a lens, quietly concentrating sunlight onto a curved paper card held in a metal frame. When the sun is strong enough and not blocked by cloud, that focused beam scorches a burn trace into the card, and the length of the scorched path corresponds to the Bolte number of hours of bright sunshine. What made the recorder so widely adopted was its ruggedness and the fact that it needs no electricity at all, yet that same simplicity brought its own quirks. The burn mark depends on solar intensity, the condition of the card, moisture, and even how an observer interprets gaps created by broken cloud. Even with these limitations, it served many weather services for a long time because it produces a continuous physical record you can archive and compare across seasons and years, letting sunlight leave behind a tangible history. A nephoscope is a specialized instrument designed to measure the direction and sometimes the speed of cloud motion in a consistent, repeatable way. Rather than relying on quick visual judgment, classic nephoscopes provide a marked surface, and an optical reference that helps an observer align the drift of clouds with calibrated lines. With careful use, the observer can convert the gentle movement of clouds into a bearing, and in some setups, into an estimate of how quickly the cloud field is sliding across the sky. Nephoscopes mattered during a period when tracking clouds was one of the few practical ways to infer winds aloft, long before widespread radiosondes and Clark. Satellite imagery made upper air flow easier to quantify. Their decline is closely tied to a changing measurement culture. Modern meteorology leans on automated ceilometers, radar, and satellite-derived wind vectors. Even so, the nephoscope remains a calm example of human-in, the loop measurement, where simple geometry, steady attention, and a reference grid turned fading sky motion into numerical data. The Cater thermometer was created to quantify how quickly a warm object loses heat to the surrounding air, an early attempt to measure the air's cooling power. It is typically an alcohol thermometer with a relatively large bulb, warmed above a set temperature, then timed as it cools between two marked points. Because the cooling rate depends on airflow, convection, and humidity, the result is not just a temperature reading, but a practical measure of how the environment draws heat away. Its usefulness was especially tied to ventilation, workplace comfort, and hygiene at a time when comfort was increasingly treated as a public health question, rather than a private impression. The Cater thermometer gradually faded as thermal comfort science moved toward standardized sensors, anemometers, and derived indices that are easier to bear, deploy, and compare. Still, it quietly shows how measurement priorities often reflect social needs like factory ventilation and disease prevention just as much as pure physics. The hair hygrometer measures relative humidity using a property that feels almost gentle in its simplicity. Human or animal hair changes length as its car. Moisture content changes. Strands of hair are tensioned within a mechanical frame, and as humidity rises, the hair lengthens slightly, shifting a linkage that moves a pointer across a scale. With careful construction, this turns a subtle biological response into a visible reading you can check at a glance. These instruments were once common in laboratories and observatories because they offered direct, immediate humidity indication without complex chemical handling. Over time, they were displaced by electronic capacitive sensors and by methods that are easier to standardize across different instruments and sites. Yet the hair hygrometer remains notable as an early example of bio-based sensing, where a living material, properly prepared and tensioned, became the precision element, long before modern biosensors made that idea feel familiar. A psychrometer estimates humidity using two thermometers, one kept dry and the other kept wet, relying on the cooling power of evaporation. The wet bulb thermometer is wrapped in a moist wick, and as water evaporates it draws heat away, lowering the wet bulb temperature relative to the dry bulb. The difference between those readings can be translated into humidity using physical principles and lookup tables, connecting moisture in the air to a measurable power. Temperature gap. In sling psychrometers, the paired thermometers are spun through the air to standardize airflow over the wet wick, helping the wet bulb reach a stable and reliable value. The psychrometer became forgotten in everyday practice, largely because it demands technique, clean wick material, distilled water, adequate ventilation, correct tables or calculations. Where it is used carefully, though, it remains a valuable benchmark for checking newer sensors and diagnosing drift because it ties humidity estimation to clear, grounded physical behavior. The classic cup anemometer, often associated with Robinson, uses 3 or 4 hemispherical cups mounted on horizontal arms so that wind turns caca, invisible flow into straightforward rotation. In early versions, the design was purely mechanical, with gear trains and counters that could log wind run over time. Instead of trying to feel gusts or judge their strength, an observer could let the instrument translate wind into a countable motion. As wind engineering matured, the limitations of this approach became clearer. Cup anemometers can overspeed in gusts, and their readings depend on bearing friction, icing conditions, and calibration choices that influence how rotation becomes an estimate of speed. Even so, the instrument shaped early climatology by making long-term wind records feasible with relatively simple hardware, creating datasets that helped people describe wind not only as a sensation, but as a quantity tracked through time. The Dines pressure tube anemometer took a different approach from cups, using pressure differences created by wind flow to infer speed. Typically, a tube faces into the wind while a reference pressure path provides comparison, and the resulting difference is linked to a measurement. In some historical variants, this pressure-based signal drove a recording mechanism so that wind speed could be traced continuously over time rather than sampled as occasional readings. Its historical significance rests in that push toward continuous wind recording, which helped meteorology move from scattered observations to time-resolved wind behavior. Pressure tube designs also quietly foreshadow the pitot-static principles later used widely in aviation and fluid measurement. Many installations eventually became museum pieces as electronic transducers and digital logging made pressure-based wind measurement more compact, less mechanically delicate, and easier to maintain without the same careful linkage systems. A pyrheliometer measures direct solar radiation from the sun along a narrow field of view, typically using a blackened receiver whose heating is measured. Historically, these instruments were central to studies of the solar constant and to atmospheric research, and they demanded careful alignment so that the instrument truly tracked the sun's direct beam. Shading control and calibration discipline mattered because small alignment and thermal details could shift results in ways that were not always obvious in the Ekachin moment. The forgotten aspect is less about the concept disappearing pyrheliometers still exist in modern monitoring networks, and more about how idiosyncratic early designs could be. Many older pyrheliometers were mechanically and thermally distinctive, and their results were strongly tied to local practices of setup, reading, and correction. In a quiet way, they show how difficult it once was to compare solar measurements across institutions before international calibration frameworks matured, made the same sun look numerically the same in different places. An anemograph is a wind instrument designed to record wind speed and sometimes wind direction continuously as a time series. Mechanical versions often paired a rotating anemometer with linkages connected to pens and rotating drums, allowing the wind to write its behavior as a trace that could be archived. Instead of recording wind as a single number, it captured gustiness, lulls, and changing intensity as shapes on paper. These instruments were gradually replaced by digital sensors and data loggers, which made recording easier, more robust, and less dependent on mechanical upkeep. Yet the historical value of an anemograph lies in the record itself. Once wind became a continuous dataset, researchers could study diurnal patterns, storm, signatures, and variability in a way that a few manual readings per day could never reveal. The instrument belongs to a broader shift in science where the goal became not just measurement, but an enduring curve of change through time. A pluviograph records rainfall intensity and accumulation over time rather than simply collecting a total for later measurement. Mechanisms varied, tipping buckets, floats, or weighing systems. But the defining feature was a continuous trace on a chart that showed how rain arrived across minutes and hours. This transformed precipitation from a daily total into a story of bursts and pauses where timing and intensity were visible. As automated electronic precipitation sensors became common, the classic chart-based pluviograph became less visible in routine work. Still, its logic remains important because hydrology and flood science depend on intensity, not just total rainfall, and a time-resolved chart can reveal sharp bursts that strongly influence runoff and erosion. In a calm way, the pluviograph represents the moment rain stopped being only how much and became how it happened. Storm glasses are sealed containers filled with solutions that form crystals under changing conditions, and they were historically associated with weather prediction in popular and maritime settings. The idea was that crystal patterns clear, cloudy, feathery, or settling correlated with upcoming changes in weather, offering a visual forecasting aid. They appealed because they seemed to turn the atmosphere into something you could watch quietly on a shelf, as if the glass itself were listening to the air. Modern meteorology does not treat storm glasses as reliable predictive instruments, and their decline reflects a shift toward measurements grounded in, quote, validated physical principles and models. Still, they remain useful to consider because they sit on the boundary between instrument and folklore. An object can be presented as a measuring device and persist culturally even when its causal reliability is uncertain or inconsistent. They remind us that the history of instruments includes not only what works well, but what people hoped might work. A Secchi disc is a simple, standardized tool for measuring water transparency. A white disc, sometimes divided into black and white quadrants, lowered into water until it disappears from view. The depth at which it vanishes, Secchi depth, serves as a practical indicator of turbidity and light penetration, linking a straightforward observation to sediment, load, water quality, and aquatic ecology. With nothing more than a disc and a line, it turns how clear the water looks into a number that can be recorded. Its enduring simplicity is also what makes it easy to underestimate. Even though modern optical instruments can quantify light attenuation with high precision, the Secchi disc created a shared observational practice that allowed long-term comparisons across sites and decades. In many environmental records, this low-tech disc remains a surprisingly valuable bridge between historical observation and modern monitoring, because the method is consistent, repeatable, and interpretable in the same way year after year. The Ettman current meter is a mechanical oceanographic flowmeter used to measure both current speed and current direction. It typically uses a propeller to respond to flow, along with a directional system that can include a compass and a recording mechanism. To control measurements at depth, messenger weights were often used to start and stop the instrument's recording sequence, allowing discrete readings at chosen depths during a deployment. What makes the Ettman meter feel forgotten today is how labor-intensive this style of measurement is compared with modern acoustic Doppler instruments that can profile currents continuously. Yet it embodies an older logic of careful sampling, discrete snapshots, each obtained with disciplined deployment, mechanical robustness, and later, interpretation of a physical record after retrieval. In its quiet mechanics, it captures a period when measuring the sea meant negotiating with depth and time through deliberate, tangible procedures. Kelvin's sounding machine used fine steel piano wire, wound on a drum, to measure ocean depth by paying out wire with a sinker weight. Compared with earlier hemp rope soundings, piano wire reduced drag and improved practicality in deep water, enabling faster and more reliable depth measurement. The deck-mounted mechanism made it possible to work with great lengths of line more predictably, pushing ocean sounding into a more systematic practice. It helped transform bathymetry by making deep sea sounding more routine and less uncertain, which mattered for navigation, ocean science, and the growing desire to map the seafloor. Its forgotten status comes from echo sounding and modern sonar, which made physical line soundings rare for general depth work. Still, historically it stands as a milestone in exploration, a manageable mechanical system that let ships reach deeper waters with a steadier, more repeatable method of finding the bottom. Milne-type seismographs, including later Milne shore designs, used a horizontal pendulum approach to record ground motion from earthquakes onto a pretty, moving surface such as paper or smoked glass. The mechanism translated tiny shifts of the ground into a trace that could be stored, compared, and exchanged across stations, supporting early networks that relied on broadly similar instruments. With careful damping and stable installation, these instruments could capture distant events, letting faraway earthquakes appear as curves in a local record. They became less central as broadband digital seismometers expanded both frequency range and dynamic range, offering a more complete and easily processed representation of ground motion. The Milne lineage is historically instructive because it shows the shift from mechanical recording, where friction, damping, and pen mechanics strongly shaped the data, electronic sensing, where calibration and signal processing dominate. Even so, those earlier traces were a crucial foundation, helping seismology become comparative and network-based rather than isolated and anecdotal. Wiechert seismographs were massive mechanical instruments that used very heavy masses, sometimes tens to hundreds of kilograms, to provide a stable inertial reference. Ground motion relative to that heavy mass was recorded, and the instrument incorporated damping systems to control oscillation and improve the bow interpretability of the resulting trace. In observatories, a Wiechert seismograph could feel like a permanent fixture, built not for portability, but for sustained sensitivity and reliability. They became forgotten not because they lacked capability, but because they were impractical compared with compact sensors that offer superior bandwidth and easier maintenance. Yet their design highlights a distinctive approach to sensitivity. If you need a stable inertial reference, one path is to build it heavier, so it resists small disturbances. In that calm, weight-driven strategy, the Wiechert instruments reveal an earlier engineering intuition. Use mass, geometry, and damping to let the Earth's motion buck draw itself onto a record. Thermoscopes were early temperature-indicating devices that showed changes without using a standardized numerical scale. Many designs relied on air expansion to move a liquid level, so warming and cooling became visible shifts rather than a reading like 20 degrees C. This made thermoscopes valuable for experiments and demonstrations at a time when temperature measurement was still transitioning from sensation and description into something physical and repeatable. They are now mostly museum objects because modern temperature sensors are ubiquitous and standardized, making temperature feel like a settled quantity. Yet thermoscopes represent an important bridge in measurement history. The move from subjective impressions of hot and cold to an observable indicator that could be shown, compared, and discussed. Even without an agreed scale, they helped establish the idea that heat could be tracked by an instrument, not only by the body. Six's thermometer, also known as the maximum-minimum thermometer, records the highest and lowest temperatures reached over a period without needing continuous observation. It uses a U-shaped tube and movable index markers that remain at the furthest points reached by the liquid, storing two memory values, the maximum and the minimum. This made it especially useful for daily climate records, where extremes mattered even if nobody was present at the exact moment they occurred. Its role diminished with automated weather stations and continuous digital logging, but the design remains a clever example of a mechanical data logger. It shows how an instrument can store information over time without electricity. The environment drives the movement, and the instrument preserves the extremes for later reading. In a gentle sense, It's a reminder that recording does not always require a pen or a file. Sometimes it's built into the way the instrument holds its own. History. Thermographs record temperature continuously, often using a bimetallic coil that expands and contracts as temperature changes. That coil drives a linkage attached to a pen, which writes onto paper wrapped around a rotating drum, producing a time-resolved record rather than isolated readings. This made thermographs valuable not only in meteorology, but also in building studies and other settings where daily cycles, sudden fronts, and rapid changes mattered as patterns through time. Thermographs became less common as digital sensors and data storage made continuous logging easier and less maintenance-heavy. Even so, their charts once provided immediate insight into thermal behavior, night cooling, midday peaks, and abrupt shifts captured as a visible curve. They belong to a broader tradition of recording instruments that turned environmental variables into physical traces that could be archived, compared, interpreted without needing complex computation. Some older recording rain gauges used float mechanisms, where a float rises in a chamber as rain accumulates. The float's upward motion can be linked to a pen so that rainfall accumulation is drawn as a curve over time, creating a continuous record rather than a single bar. Collected total. Compared to a simple collecting gauge read once per day, this provides a smoother picture of when rain arrived and how quickly it built up. These float systems became less common as tipping bucket data loggers and weighing gauges improved reliability and reduced maintenance burdens. Yet they illustrate a classic compromise in instrumentation: smoother accumulation traces in exchange for mechanical complexity and vulnerability. To practical problems. Debris, algae growth, freezing conditions, and general upkeep could all interfere with motion, reminding us that continuous recording often brings a quiet cost. The instrument must remain clean, free, and responsive over long exposure to the environment. Fortin-style mercury barometers use an adjustable system and a small ivory point reference to set a consistent zero level for the mercury surface. Before taking a reading, the observer adjusts the system until the mercury meniscus just touches the ivory point, and only then reads the column height precisely. This procedure is designed to control a tricky physical variable, exact mercury level, so that readings are comparable and systematic error is reduced. The method improved precision, but it demanded careful technique and a practiced eye, because the quality of the reading depends on the consistency of that adjustment. Ritual. Instruments like these became less common as aneroid and electronic pressure sensors offered safer and simpler alternatives without exposed mercury. Still, Fortin-style adjustment highlights a quiet truth about older precision instruments. Accuracy often depended not only on the hardware, but on disciplined operation designed to tame the subtle behaviors of real materials. The Dubosc colorimeter is a classic optical instrument designed to compare the concentration of a solution against a standard by balancing their apparent color, intensity. Instead of changing chemistry, it changes geometry. The path length of light through each liquid can be adjusted independently. By raising or lowering the columns of sample and reference until both fields appear equally bright, the observer reaches a visual null point. The ratio of the path lengths then reveals the relative concentration, grounding the result in proportional geometry rather than subjective estimation of darkness. What made the Dubosc colorimeter especially valuable in its time was this reliance on equality rather than judgment of magnitude. The observer does not decide which sample is darker, only when the two are the same, which often improves repeatability. As photoelectric detectors and digital spectrophotometers became common, visual null instruments like the Dubosc gradually disappeared from routine. Laboratories. Yet it remains an elegant example of how careful optical design can compensate for the limits of human perception by turning measurement into a calm act, balance. The Lovibond tintometer measures color using a library of standardized colored glass filters that can be stacked in combination. A sample is viewed alongside these reference glasses, and the operator adjusts the stack until the perceived color matches as closely as possible. Each glass has a known value, so the final combination corresponds to a reproducible color specification tied to physical standards rather than descriptive chow. Language. This instrument played an important role in industries where color consistency mattered long before electronic colorimeters were affordable or portable. Oils, brewing products, foodstuffs, and chemicals could be checked quickly using a visual comparison rooted in standardized materials. Over time, electronic spectrophotometers replaced tintometers by removing observer bias and expanding precision. Still, the Lovibond system shows how industrial measurement often begins with tangible references: glass, light, and the eye, before moving into digital B. Abstraction. Nessler tubes are tall, matched glass columns used for visual color comparison in chemical testing. A sample and a standard solution are placed into identical tubes, and the observer compares color intensity by looking down through the liquid column. Because the path length is fixed and relatively long, even faint color differences become more apparent, allowing semi-quantitative estimation of concentration. These tubes were widely used in water testing and analytical chemistry, especially where low-level color reactions were involved. Their decline came with the spread of photometers that could quantify absorbance objectively and quickly. Yet Nessler tubes illustrate a careful exploitation of geometry. If your detector is the human eye, extending the optical path is a simple way to amplify sensitivity without adding complexity. Hainer tubes are similar in spirit to Nessler tubes, but were optimized for detecting extremely faint color in liquids by using especially long optical paths. The longer the column of liquid, the more cumulative absorption affects transmitted light, making tiny differences visible. This approach allowed analysts to push visual detection toward lower concentration limits. As with many visual methods, Hainer tubes were eventually displaced by electronic detection that could reach lower limits with greater consistency. Their historical importance lies in showing how analytical chemistry once leaned heavily on controlled viewing conditions, standardized glassware, and disciplined cow. Observation to extract quantitative meaning from subtle visual cues. The Heligay colorimeter represents a family of rugged visual comparator instruments used for quick field and bench testing. Many designs use prisms or split-view optics that place a sample and reference side by side in a single field of view, often with built-in permanent color standards. This arrangement minimizes lighting differences and helps the observer focus on direct comparison. Such instruments were valued for portability and speed rather than ultimate precision. As digital colorimeters became smaller, cheaper, and easier to calibrate, Heligay-style visual comparators faded from common use. Still, they capture an important moment in measurement history where practicality and robustness mattered more than high-resolution data, especially outside DAO. Controlled laboratory environments. Early turbidity comparators often adapted colorimeters by adding black sleeves or jackets around the sample cell to block stray light. By controlling the viewing geometry, these setups allowed observers to judge how much light was lost due to suspended particles rather than dissolved color. The method relied on consistent illumination and careful handling to produce comparable results. These hybrid instruments rarely appear as a single named device, which is why they are easily forgotten. Their significance lies in how measurement often evolves incrementally by modifying existing tools rather than inventing entirely new ones. A color comparator becomes a turbidity tool once the optics are constrained in the right way. The Stokes Recorder is an early air pollution instrument that draws a known volume of air through filter paper, capturing soot and particulates as a dark stain. Over time, the darkness of the stain provides a record of particulate pollution, either through visual comparison or later optical measurement. Instead of counting particles directly, it integrates exposure over time. These instruments were especially important in early urban air quality studies, when continuous electronic monitoring did not exist. As modern particle counters and chemical analyzers took over, smoke stain recorders became rare. Yet they established a crucial concept. Time-integrated sampling can reveal chronic exposure patterns that short-term measurements might miss. The deposit gauge measures how much particulate matter settles out of the air over time into a container. Unlike instruments that measure airborne concentration, deposit gauges capture what actually accumulates on surfaces: dust, soot, and industrial fallout over weeks or months. This made them useful for documenting nuisance pollution and material soiling. Their use declined as regulatory focus shifted toward inhalable particle concentrations and health metrics. Still, deposit gauges provide a different environmental perspective, reminding us that pollution is not only what we breathe, but also what quietly settles and accumulates around us. Early ozone bubbler samplers measured ozone by drawing air through a chemical solution that reacts with ozone to produce a measurable color change. The system required controlled airflow, stable reagents, and careful timing, turning an invisible reactive gas into a quantifiable chemical signal. As UV photometric ozone analyzers became standard, these wet chemical methods fell out of routine use. Their historical value lies in teaching laboratories how sampling itself can influence results reaction rates, flow control, and reagent stability, all P. Mattered long before digital displays simplified the output. The arsine generation apparatus used in classical arsenic detection converted trace arsenic in samples into arsine gas, which was then decomposed or reacted to produce a visible stain. This allowed detection of very small quantities at a time when other analytical options were limited. These setups became obsolete due to safety concerns and the rise of instrumental methods like atomic absorption spectroscopy. Yet they illustrate how early toxicology often relied on transforming a hidden contaminant into a visible form through controlled chemical pathways rather than DAO. Electronic sensing. The blowpipe analysis kit was a portable microanalytical system used by mineralogists to identify elements by heating tiny samples in a flame. Observers watched flame colors, bead formation with fluxes, and residue behavior to infer composition, often in the field. As spectroscopy replaced visual flame tests, blowpipe analysis declined. Its historical importance is that it enabled chemical insight without a laboratory, showing how heat, observation, and experience could substitute for complex instrumentation when portability mattered most. The crystal goniometer measures angles between crystal faces, supporting systematic classification in mineralogy and crystallography. Early contact goniometers touched crystal faces directly, while reflecting goniometers used optical reflection for far higher precision. With the rise of X-ray diffraction, surface angle measurement became less central. Still, goniometers were foundational, allowing crystals to be categorized numerically long before their internal lattice structures could be probed directly. Abney's clinometer measures angles of slope and elevation using a sighting system and an internal bubble level. It was widely used in geology, forestry, and surveying where quick angle estimates were needed under field conditions. Digital inclinometers eventually replaced it, but Abney's clinometer demonstrates how optical sighting and gravity references could be combined into a BOO, compact, reliable field instrument long before electronics made such measurements trivial. The hypsometer estimates altitude by measuring the boiling point of water, which decreases as atmospheric pressure falls. By observing boiling temperature with a thermometer, the instrument infers elevation without directly measuring pressure. It became less common as barometric altimeters and GPS spread. But the hypsometer shows a clever indirect approach to measurement, using a phase change temperature as a proxy for pressure, when pressure itself was difficult to read accurately in the field. The thermopile radiometer uses many thermocouples connected in series to convert tiny temperature differences into a measurable voltage. When radiation warms an absorbing surface, the thermopile amplifies that effect electrically. These instruments were important in early infrared research and radiometry. Although modern detectors offer greater sensitivity, thermopiles remain a reminder that electrical amplification once began with careful thermal design. The thermoscope predates standardized thermometers and indicates temperature change without numerical scale. Often based on air expansion moving a liquid, it made warming and cooling visible rather than measurable in degrees. Its importance lies in conceptual transition, showing that heat could be tracked by an instrument even before agreement on units or scales existed. The cathetometer measures small vertical distances using a telescope mounted on a precision vertical scale. It was widely used to measure liquid menisci, capillary rise, and dimensional differences in physics experiments. Though digital displacement sensors replaced it, the cathetometer highlights how separating observation from measurement site first, then read, can improve precision in delicate experiments. The sonometer studies vibrations of a stretched string by adjusting length and tension to explore frequency relationships. By observing resonance and harmonics, it connects sound to physical parameters directly. While modern signal generators replaced it in many labs, the sonometer remains a clear mechanical demonstration of the laws of vibration. The grid dip meter detects resonance in nearby circuits by showing a dip in oscillator output when energy is absorbed. It allowed radio technicians to find resonant frequencies without direct electrical connection. As spectrum analyzers became common, grid dip meters faded from routine use, but they remain a classic hands-on tool for understanding resonance through coupling rather than direct measurement. The Q meter measures the quality factor of inductors and resonant circuits, revealing how sharply they resonate and how much energy they lose. This mattered greatly in early radio design, where selectivity and efficiency depended on high Q components. Modern impedance analyzers replaced dedicated Q meters, yet they represent a period when component quality required specialized instruments, tailored to analog RF behavior. The Johansen microcator is a mechanical comparator that amplifies tiny dimensional changes using a twisted strip mechanism. It converts micrometer-scale motion into readable pointer movement without electronics. Its decline came with electronic displacement sensors, but it stands as a testament to how mechanical ingenuity once achieved extraordinary sensitivity through geometry alone. The polariscopic strain viewer is an optical instrument used to visualize internal stresses in transparent materials by exploiting birefringence. When a stressed plastic or glass object is placed between crossed polarizers and illuminated, stress patterns appear as bands or fringes of light and color. These patterns reveal how forces flow through a material, highlighting stress concentrations around holes, edges, and load-bearing regions that might otherwise remain invisible. Before computer simulation and digital photoelastic systems, these viewers were essential in engineering design and failure analysis. They allowed designers to see stress rather than infer it purely from calculation, guiding safer shapes and load paths. Their decline reflects the rise of numerical modeling and automated imaging, yet the underlying idea remains powerful. Light, when carefully controlled, cantanti reveal hidden mechanical stories inside solid matter. The Tupelo-Schlieren apparatus is an optical system designed to make variations in refractive index visible, revealing density gradients in transparent media such as air or other gases. Using lenses, a focused light source, and a knife edge, the system converts tiny deflections of light caused by temperature or pressure differences into visible brightness variations. This makes shock waves, thermal plumes, and mixing flows appear as luminous structures against a dark background. Schlieren systems became central to early aerodynamics and heat transfer research, especially where inserting probes would disturb the phenomenon being studied. Although modern digital Schlieren and computational methods have taken over many applications, classical setups are less commonly encountered due to their sensitivity to alignment and vibration. Still, they remain a calm demonstration of how optics can translate the invisible motion of fluids into visible form without touching the flow at all. The interference refractometer measures refractive index with high precision by observing shifts in interference patterns when a sample is introduced into an optical path. Instead of relying on simple refraction angles, it uses the extreme sensitivity of interference fringes to detect very small changes in optical path length. This made it possible to measure subtle variations in composition, purity, or temperature effects on refractive properties. As digital refractometers and spectroscopic techniques advanced, classical interference refractometers became less common outside specialized research. Their historical importance lies in demonstrating how wave behavior rather than ray geometry can be harnessed for precision measurement. They show a gentle shift in instrumentation philosophy, from seeing light as a straight path to using its interference as a ruler of extraordinary fineness. The Abbe refractometer is a benchtop optical instrument that measures refractive index using the principle of the critical angle at an interface. A sample is placed between prisms, illuminated, and viewed through an eyepiece where a sharp boundary appears. By aligning this boundary with crosshairs, the operator reads the refractive index directly from a calibrated scale. For decades, AB refractometers were standard tools in chemistry, food science, and industry, especially for checking oils, sugars, and solutions. While many are still in use, their prominence has declined, as digital refractometers offer automated temperature compensation and readout. Yet the Abbe design remains a model of clarity, showing how a single optical boundary can anchor a reliable, repeatable measurement. The polar planimeter is a mechanical instrument that measures the area of irregular shapes by tracing their outline. As the tracer moves, a system of arms and a rolling wheel integrates the motion, producing a direct area reading. Engineers, cartographers, and scientists used it to compute areas on maps, charts, and graphs without breaking shapes into simpler components. Its decline followed the rise of computer-based integration and digital image analysis. Still, the polar planimeter represents a remarkable physical embodiment of calculus, where integration happens through constrained motion rather than algebra. It quietly demonstrates that mathematical operations can live inside mechanisms, turning movement into meaning without any written calculation. The intergraph is a mechanical device that goes one step further than the planimeter by drawing the integral of a plotted curve. As the operator traces a function, the machine produces a new curve representing accumulated area. Through linkages, wheels, and guides, the instrument performs continuous integration in real time. Once electronic computation became widespread, intergraphs faded into obscurity. Yet they are historically important as analog computers, machines that solved mathematical problems by physical behavior rather than symbolic manipulation. They reveal a time when solving equations could mean building a mechanism and letting it move slowly and faithfully into an answer. The pantograph is a linked arm drawing instrument, that copies figures at different scales while preserving proportions. In scientific work, pantographs were used to enlarge or reduce maps, anatomical drawings, and instrument diagrams accurately. By adjusting pivot points, users could control the scaling factor with mechanical certainty. As photography and digital scaling took over, pantographs became rare in laboratories. Still, they represent an important stage in scientific communication, where accurate visual scaling mattered deeply because drawings often carried quantitative information. The pantograph shows how geometry and motion once ensured fidelity long before pixels did. The camera lucida is an optical attachment that projects an image from a microscope or scene onto a drawing surface, allowing an observer to trace features accurately. In microscopy, this enabled scientists to produce scale-accurate drawings of cells, tissues, and organisms when photography was slow, expensive, or limited. In contrast, although digital imaging replaced most camera lucida use, its historical role was significant. It turned observation into documentation without forcing the observer to rely on memory or freehand estimation. The instrument quietly shaped how biological and medical knowledge was recorded, where careful drawings served as authoritative records rather than illustrations. The heliograph in meteorology uses sunlight to record time or solar presence, often by focusing the sun's rays onto a recording surface that burns or marks as the sun moves. Unlike clocks, it relies entirely on celestial motion, letting the sky itself drive the measurement. These instruments became less common as precise clocks and electronic logging spread. Historically, they show how natural cycles were once used directly as measurement engines. The heliograph transforms the sun from an object of study into an active participant in recording, marking time through its own movement. The plumb bob may appear simple, but as part of scientific measurement systems, it provided a reliable reference for vertical direction based on gravity. In surveying and instrument alignment, it ensured that measurements were anchored to a consistent physical direction, stabilizing setups across uneven terrain. Its forgotten nature comes from how fundamental it is often unnoticed despite its importance. Even today, many precision instruments rely on gravity-based references, whether explicit or hidden inside sensors. The plumb bob reminds us that some of the most important measurement tools are the quietest ones. The meridian line, built into architecture, uses a small aperture to project the sun's image onto a line marking true north-south alignment. Over the year, the sun's image shifts along the line, revealing seasonal changes and allowing calibration of clocks and calendars. These large-scale instruments faded as timekeeping became portable and independent of solar observation. Yet they represent a unique fusion of science and architecture, where buildings themselves became measuring devices. The meridian line shows how permanence and scale can be used to achieve long-term observational stability. The photographic plate measuring engine converts astronomical images on glass plates into precise numerical data. With a microscope mounted on a precision stage, operators could measure star positions relative to reference marks, turning dots of light into coordinates. These machines became obsolete with digital detectors and automated astrometry. Historically, they highlight that data collection and data extraction are distinct tasks, each requiring its own instrument. The telescope captured the sky, the measuring engine made it measurable. The blink comparator rapidly alternates between two images of the same field to reveal motion or change. Asteroids, variable stars, and other transient phenomena appear as flickering or shifting points, exploiting the human eye's sensitivity to movement. Though digital difference imaging now dominates, blink comparators was central to discovery for decades. They show how instrumentation can amplify cognitive strengths, turning perception itself into a detection method guided by mechanical rhythm. Waveform recording on smoked paper uses a subcoated surface and a light stylus to capture delicate signals with minimal friction. As the recording surface moves, the stylus scratches away soot, leaving a clear trace of motion or pressure. This technique was essential in physiology and mechanics, where heavy pens would distort signals. Though replaced by electronic recording, it illustrates a core principle of measurement. The recorder must interfere as little as possible with what it records. The pneumograph records breathing by converting chest or abdominal motion into a trace. Belts, levers, or flexible tubes capture expansion and contraction, producing a continuous curve of respiratory rhythm. Its historical value lies in making an internal physiological process visible and comparable. Modern sensors replaced it, but pneumographs helped establish respiration as a measurable, analyzable signal rather than a subjective observation. The merry tambo converts pressure changes into motion using a flexible membrane and lever system. When coupled to a recorder, it transforms pressure variations like pulse waves into readable curves. Though electronic transducers replaced it, the timbre standardized pressure recording in early physiology. It shows how careful mechanical design once bridged the gap between living systems and quantitative analysis. The string galvanometer uses a fine conductive filament suspended in a magnetic field to detect tiny currents. Small electrical signals deflect the string, and optical magnification makes the movement recordable. It enabled early bioelectric measurements before electronic amplification was practical. The string galvanometer demonstrates how reducing mass and friction can unlock sensitivity, letting faint signals speak clearly. The early electrocardiograph was a system combining electrodes, sensitive galvanometers, timing references, and recording mechanisms. Operating it required careful preparation, but it produced a reproducible trace of heart activity. As devices became compact and automated, these complex systems disappeared. Yet they mark a turning point where internal biological rhythms became measurable data, bridging physiology and clinical practice. The cathetometer measures small vertical distances using a telescope and precision scale. It was used to read meniscus heights, capillary rise, and dimensional differences with high accuracy. Its replacement by digital sensors does not diminish its instructional value. The cathetometer shows how separating observation from measurement can improve precision, especially when dealing with subtle physical features. The sonometer studies string vibration by controlling length and tension to explore frequency relationships. Resonance and harmonics become directly observable as sound and motion. Though largely replaced by electronic tools, it remains a clear mechanical expression of acoustic physics. The sonometer demonstrates how fundamental laws can be explored through simple, repeatable setups. The Q-meter measures how sharply a circuit resonates, revealing energy loss and selectivity in radio components. Early radio engineering relied on such measurements to optimize performance. Modern analyzers replaced dedicated Q-meters, but their role was crucial in analog electronics. They remind us that component quality once required instruments tailored specifically to subtle energy behavior. The Johansen microcator is a mechanical comparator that amplifies tiny dimensional changes using a twisted strip mechanism. It turns micrometer-scale movement into readable pointer deflection without electronics. Its decline followed the rise of electronic sensors, but it remains a striking example of mechanical sensitivity. Geometry alone, carefully arranged, can magnify the smallest motions into reliable measurements. The absorption wave meter is an early radio frequency instrument that determines frequency by exploiting resonance rather than direct counting. It contains a tunable resonance circuit placed near a transmitter or signal source, and as the circuit is adjusted, it absorbs energy most strongly when it reaches resonance with the unknown frequency. This absorption appears as a noticeable dip in signal strength on a connected meter, creating a clear condition that marks the matching frequency. What made absorption wave meters useful was their simplicity and robustness at a time when precise electronic frequency counters did not yet exist. They required careful calibration and a stable resonant circuit, and the accuracy depended on component quality and temperature stability. As modern digital counters became inexpensive and extremely precise, absorption wave meters gradually disappeared from routine use. Still, they illustrate a calm and elegant measurement philosophy. Rather than measuring frequency directly, let the system reveal it through resonance and energy transfer. The precision wave meter represents a more refined version of resonance-based frequency measurement, designed specifically for calibration and standards work in radio laboratories. These instruments emphasized mechanical rigidity, high-quality inductors and capacitors, and carefully engraved scales so that resonant frequency could be read with greater confidence. Shielding and stable construction reduced drift, making them suitable as reference devices in workshops and broadcasting facilities. Their decline followed the widespread adoption of crystal oscillators and electronic frequency standards, which offered far superior stability and ease of use. Yet, precision wave meters played an essential transitional role, allowing radio systems to be tuned and compared consistently. They demonstrate how frequency, long before digital readouts, was treated as a physical property that could be found by carefully matching resonance conditions. The grid dip meter, also known as a dip oscillator, is a compact RF instrument used to locate resonant frequencies of nearby circuits without direct IC. Electrical connection. It contains a small tunable oscillator with interchangeable coils, and when brought close to another resonant system, energy coupling causes a drop or dippy in oscillator amplitude at resonance. This visual cue allows technicians to identify resonant points quickly and intuitively. Grid dip meters became beloved tools for radio amateurs and engineers because they were fast, flexible, and required little setup. Although modern spectrum analyzers and network analyzers have replaced them in professional settings, the grid dip meter remains a classic example of hands-on measurement. It shows how proximity and coupling can replace wiring, and how resonance itself can act as the indicator. The decrometer measures damping in oscillatory circuits by assessing how quickly oscillations decay. In early radio engineering, understanding damping was crucial for controlling bandwidth, interference, and signal clarity. Decrometers provided insight into how clean or persistent an oscillation was, linking circuit losses to practical performance. As electronic test equipment advanced, decrometers became obsolete, absorbed into more comprehensive RF analyzers. Historically, though, they remind us that early radio measurement focused not only on frequency and power, but also on how energy behaved over time. The instrument quietly emphasized that the quality of oscillation mattered as much as its pitch. The Q meter measures the quality factor of resonant circuits, indicating how sharply they resonate and how much energy they lose per cycle. By applying a known RF signal and observing voltage magnification at resonance, the instrument provides a direct measure of circuit efficiency and selectivity. Q meters were indispensable in mid-century radio design, where receiver performance depended on narrow bandwidth and high Q components. Although modern impedance analyzers have replaced dedicated Q meters, their role highlights a period when component behavior had to be carefully characterized with specialized instruments tuned to analog realities. The bridge circuit, especially the Wheatstone bridge, became a foundational measurement system for detecting very small changes in resistance. By balancing two legs of a circuit against each other, tiny deviations produce measurable imbalance signals. This principle underlies strain gauges, temperature sensors, and many other detection systems. While today the bridge often exists invisibly inside electronic instruments, its historical importance is immense. It enabled precise measurement by comparison rather than absolute reading, reducing sensitivity to noise and drift. The bridge illustrates a quiet measurement truth. Balance can be more powerful than direct measurement. The extensometer measures how much a material stretches under load, converting tiny elongations into readable values. Early mechanical extensometers used lever systems, knife edges, and dial indicators to amplify small length changes during tensile testing. Their use established quantitative stress-strain relationships that define material properties like elastic modulus and yield strength. Though electronic strain gauges now dominate, mechanical extensometers remind us how material science became numeric by turning deformation into a AA. Measurable, repeatable signal. The Brinell hardness tester measures hardness by pressing a hardened ball into a material and measuring the resulting indentation. The size of the indentation combined with applied force yields a hardness value that reflects resistance to deformation. This method helped standardize hardness testing across industries long before automated systems existed. Although modern machines simplify the process, the Brinell test remains a calm example of how controlled force and geometry can translate tactile resistance into a numerical property. The Rockwell hardness tester determines hardness by measuring indentation depth rather than diameter. Using a minor load followed by a major load, it produces a direct hardness reading without requiring optical measurement of the indentation. Its speed and practicality made it popular in factory environments. Early mechanical Rockwell testers demanded precise load application and careful surface preparation, highlighting how even quicker tests rely on disciplined albor. Technique to remain meaningful. The Shaw scleroscope measures hardness dynamically by dropping a small hammer onto a surface and measuring rebound height. Harder materials return more energy, producing higher rebounds. Although sensitive to surface finish and sample mass, it offered a rapid comparative hardness test. The scleroscope illustrates an alternative measurement, velocity energy return rather than static deformation, showing that the same property can be probed through different physical behaviors. The ultramicroscope detects particles smaller than optical resolution by observing scattered light in dark-field illumination. Particles appear as bright points against darkness, revealing their presence without resolving shape. It played an important role in colloid science before electron microscopy. The ultramicroscope shows how detection does not always require resolution. Sometimes visibility through interaction is enough. The opsisometer measures curved distances on maps by rolling a small wheel along a path. Each wheel rotation corresponds to a known length, converting motion into distance. Though replaced by digital mapping tools, it exemplifies analog integration. The instrument quietly turns following a line into a quantitative result, linking hand movement to numerical distance. The map measurer is a related distance tool used widely in engineering and planning. Often including multiple scales, it allowed users to read real-world distances directly from maps. Its historical value lies in practicality rather than ultimate precision. It supported decision-making in logistics and planning, showing how measurement often serves applied needs rather than laboratory ideals. The optical bench provides a stable, aligned platform for optical experiments. By holding lenses, mirrors, and prisms along a defined axis, it ensures repeatable geometry and controlled spacing. While modern optical tables dominate today, classic benches help turn optics into a modular science. They show how controlling geometry is itself a form of measurement discipline. The Michelson interferometer, beyond theory, served as a working displacement and wavelength measurement tool. Fringe shifts correspond to fractions of a wavelength, making tiny movements visible. Older manual setups demanded environmental calm and patience. They reveal how high precision once depended on stillness and careful observation as much as on mathematical insight. The Fizeau interferometer measures surface flatness through interference fringes formed between a reference and test surface. Fringe patterns act as contour maps of surface error. Its role in optical fabrication linked craftsmanship to measurement feedback. Even today, its principle remains central to surface testing. The knife-edge Foucault test uses shadows to reveal curvature errors in mirrors. By cutting into the returning beam, surface deviations appear as changing illumination. This low-cost yet sensitive method democratized optical testing. It shows how geometry and light alone can reveal precision without complex equipment. The polar clock, or polar dial, uses Earth's rotation axis to keep solar time with nearly uniform shadow motion. Aligned correctly, it provides a steady temporal reference. Though obsolete for daily timekeeping, it highlights how geometry and astronomy once anchored time measurement directed to the sky. The equatorium is a mechanical device for computing planetary positions using geometric models. By setting components according to dates, it produces approximate longitudes physically. It embodies calculation as motion rather than arithmetic. The equatorium reminds us that prediction once lived inside instruments, not software. The tide gauge with float and stilling well records, sea level changes over time. The stilling well damps waves, allowing the float to track true tidal motion. Before electronic sensors, this design enabled long-term tidal records essential for navigation and coastal engineering. It demonstrates physical signal filtering built directly into instrument geometry. The audiometer is a diagnostic instrument designed to measure hearing sensitivity across a range of frequencies and intensities. Early audiometers were largely mechanical or electromechanical, producing pure tones that could be adjusted manually while the subject indicated when sounds became audible. By systematically varying frequency and loudness, the instrument produced an audiogram, a visual map of hearing thresholds that revealed patterns of hearing loss, linked to age, disease, or noise exposure. Before digital signal processing, audiometry depended heavily on calibration discipline, quiet test environments, and consistent human response. Small errors in tone generation or headphone placement could influence results, which meant trained operation was essential. Despite being replaced by computerized systems, early audiometers were foundational in transforming hearing from a subjective complaint into a measurable parameter. Sensory function with repeatable clinical meaning. The olfactometer measures the sense of smell by delivering controlled concentrations of odorants to a subject. Classical olfactometers relied on carefully diluted chemical vapors mixed with clean air, allowing experimenters to determine detection thresholds. Discrimination ability. The instrument translated an inherently subjective sensation into a structured test by standardizing stimulus strength and delivery timing. Its use highlighted the complexity of sensory measurement, where adaptation, fatigue, and psychological expectation can influence results. Modern olfactometry uses automated flow control and standardized odor panels, but early instruments established the principle that smell like vision, and hearing could be studied quantitatively. They quietly expanded sensory science beyond what could be seen or heard. The aesthesiometer measures tactile sensitivity by determining the minimum distance at which 2 points touching the skin are perceived as separate. Often consisting of adjustable calipers or paired probes, it allowed clinicians to map variations in skin sensitivity across the body. These measurements revealed differences between regions and helped diagnose nerve damage or neurological conditions. Its decline reflects the rise of imaging and electrophysiological techniques. But the aesthesiometer remains conceptually important. It demonstrates how perception itself can be probed with simple geometry, translating neural processing into spatial thresholds that can be recorded and compared. The algometer quantifies pain sensitivity by applying controlled pressure to tissues until discomfort is reported. Early mechanical algometers used springs or weights to standardize applied force, turning pain into a threshold measurement rather than a vague sensation. This helped researchers compare pain responses across individuals and conditions. Pain measurement is inherently complex, influenced by psychology, context, and expectation, which limited algometer precision. Still, these instruments marked an important attempt to treat pain scientifically, acknowledging variability while seeking repeatable reference points. The spirometer measures lung volume and airflow by capturing exhaled air and translating it into volume readings. Early spirometers used bell and water designs, where air displaced a floating chamber whose movement was recorded. This allowed assessment of vital capacity and respiratory health in both clinical and occupational settings. Their development linked respiratory physiology to public health, especially in evaluating the effects of industrial work and disease. Modern electronic spirometers replaced bulky designs, but the fundamental idea quantifying breath remains unchanged. The plethysmograph measures changes in volume within an organ or limb, often related to blood flow. Early versions used air or water-filled chambers that responded to subtle expansions and contractions. These volume changes were then recorded as curves over time. Such instruments helped establish circulation as a dynamic process rather than a static quantity. Though modern imaging offers more detail, plethysmographs demonstrated that even small physiological rhythms could be captured mechanically and studied quantitatively. The electromyograph records electrical activity produced by muscles during contraction. Early systems relied on surface or needle electrodes connected to sensitive amplifiers and recording devices. The resulting traces revealed timing, strength, and coordination of muscle activation. Before digital signal analysis, interpreting these recordings required skill and experience. Early electromyography helped bridge physiology and neurology, turning muscle action into electrical patterns that could be compared across conditions. The ergograph measures muscular work and fatigue by recording repeated contractions against a known load. Typically involving finger or hand movements lifting weights, it produced curves showing declining force over time. This made fatigue visible as a gradual change rather than an abstract feeling. Its use contributed to early studies of work physiology and human performance. Though replaced by more comprehensive systems, the ergograph illustrates how simple repetitive tasks can reveal deep insights into muscular endurance. The sphygmograph records the pulse wave by translating arterial motion into a mechanical trace. Early designs used levers resting on the skin above an artery, connected to pens that route pulse contours onto moving paper. These traces provided insight into cardiovascular health before blood pressure cuffs and electronic monitors became standard. The sphygmograph shows how clinicians once read the pulse not just by touch, but by shape and timing. The electroencephalograph EEG records electrical activity of the brain using scalp electrodes. Early EEG systems were large, delicate, and sensitive to noise, requiring controlled environments and careful electrode placement. Despite technical limitations, early EEG transformed neuroscience by revealing rhythmic brain activity. It made mental states observable as patterns, laying groundwork for modern neurodiagnostics. The kymograph is a general-purpose recording instrument that uses a rotating drum to capture physiological signals over time. Pressure, motion, or electrical changes could be recorded as continuous traces, creating a visual history of activity. Though replaced by digital acquisition, the kymograph was central to experimental physiology. it standardized time-based recording, making comparison and repetition possible across experiments. The ophthalmometer measures curvature of the cornea by analyzing reflected images. Bailey designs projected patterns onto the eye and observed their distortion, allowing calculation of corneal shape. This supported the development of corrective lenses and eye surgery. Modern corneal topographers replaced it, but the ophthalmometer established optical measurement as a clinical tool. The retinoscope assesses refractive error by observing reflections from the retina as light is moved across the eye. Changes in reflection behavior reveal whether the eye is myopic, hyperopic, or astigmatic. Though simple in appearance, accurate use requires training. The retinoscope remains conceptually important, showing how dynamic optical interaction reveals internal properties. The ophthalmoscope allows direct observation of the retina by directing light into the eye and viewing reflected structures. Early versions required careful alignment and darkened rooms. Its invention transformed eye medicine by making internal anatomy visible in living patients. Even with modern imaging, it remains a fundamental diagnostic concept. The aesthesiograph maps sensory thresholds across the skin by recording responses to stimuli. Variations in sensitivity could be plotted spatially, creating sensory maps. Such instruments highlighted that sensation is not uniform. They helped link peripheral nerve function to central processing. The tachistoscope presents visual stimuli for very brief, controlled durations. By limiting exposure time, it probes perception, recognition, and attention processes. Early tachistoscopes advanced experimental psychology, showing how much information the mind can process in fractions of a second. The pupillometer measures pupil size and response to light. Early designs used optical comparators or photographic methods to capture dilation changes. These measurements linked neurological function to observable reflexes, contributing to diagnostics long before imaging technologies. The galvanic skin response meter measures changes in skin conductance associated with sweating and arousal. Early systems amplified tiny electrical changes across the skin. This instrument linked physiology to emotional and cognitive states, forming the basis for psychophysiological research. The electrogastrograph records electrical rhythms of the stomach. Early attempts were technically challenging due to weak signals and interference. Despite limitations, they revealed that digestion has rhythmic electrical patterns, expanding electrophysiology beyond nerves and muscles. The phonocardiograph records heart sounds using microphones and amplifiers, translating auscultation into visual traces. This allowed analysis of murmurs and timing relationships. Before echocardiography, it provided a bridge between listening and measurement, preserving sound as data. The actigraph is an instrument designed to record patterns of movement over long periods, often used to study daily activity and rest cycles. Early mechanical actigraphs typically involved a wearable component connected to a recording system, where motion would trigger levers or switches that marked activity on a rotating drum or chart. Over days or weeks, this produced a visual rhythm of movement and stillness, revealing cycles that might otherwise go unnoticed. Its importance lies in showing that behavior itself can be treated as a measurable signal unfolding over time. Long before digital wearables and accelerometers, actigraphs helped establish the scientific study of circadian rhythms, sleep-wake cycles, and fatigue. They remind us that slow, repeated patterns rather than isolated events often carry the most meaningful physiological information. The chronoscope is a precision timing instrument developed to measure very short time intervals, particularly in psychological and physiological experiments. Early chronoscopes used electromagnetic or mechanical systems to start and stop timing based on stimulus presentation and subject response, allowing reaction times to be measured in milliseconds. This transformed mental processes into measurable temporal quantities. Chronoscopes demanded careful calibration and control, as small mechanical delays could influence results. Despite being replaced by electronic timers and computers, they were crucial in establishing reaction time as a scientific variable. The instrument marks a moment when thought and response began to be studied not just qualitatively, but as events unfolding in precise time. The hip chronoscope, a refined version of early timing devices, improved accuracy by using electromagnetic control to reduce mechanical lag. It became a standard tool in experimental psychology laboratories for decades, supporting studies of attention, perception, and motor response. Its decline came with electronic circuits that eliminated many sources of timing error. Still, the hip chronoscope represents a careful negotiation between mechanics and electricity, showing how precision timing emerged gradually through layered L. Technological refinement rather than a single invention. The reaction time key, often paired with chronoscopes, allowed subjects to respond to stimuli by pressing or releasing a button connected to the timing circuit. The physical design of the key spring tension, travel distance, contact quality directly influenced measured times. This highlights an often overlooked aspect of measurement. The interface between human and instrument matters. Reaction time keys show how experimental results depend not only on what is measured, but on how the subject interacts with the measuring system. The dynamometer measures force or torque, commonly used to assess muscular strength. Early hand dynamometers relied on springs or hydraulic systems, translating grip force into a needle movement or pressure reading. They allowed strength to be compared numerically across individuals and over time. While modern electronic force sensors dominate today, early dynamometers were important in occupational health, military screening, and clinical assessment. They illustrate how physical effort became quantifiable, moving strength from subjective impression to recorded value. The myograph records muscle contraction by translating mechanical shortening into a graphical trace. Classical myographs used levers attached to muscles or tendons, with movement recorded on a rotating drum. This allowed timing, duration, and amplitude of contraction to be studied precisely. Myographs helped establish fundamental principles of muscle physiology, such as latency and fatigue. Though invasive versions are no longer used, they show how motion itself can be converted into data when coupled to careful recording systems. The ballistocardiograph records the tiny movements of the body caused by the heart ejecting blood with each beat. Early systems used suspended tables or sensitive platforms that responded to these recoil forces, producing waveforms linked to cardiac output. These instruments sought to extract cardiovascular information without invasive probes. Although imaging and echocardiography eventually replaced them, ballisticardiographs represent a subtle measurement approach detecting internal function through whole body motion. The phonendoscope is a modified stethoscope designed to amplify high-frequency sounds, often using membranes or resonant chambers. It aimed to enhance subtle acoustic details that might be missed with standard auscultation. Its limited adoption reflects how amplification alone does not always improve diagnostic clarity. Still, the phonendoscope illustrates ongoing attempts to refine sensory instruments, pushing the limits of what the human ear can detect with mechanical assistance. The tachograph measures speed over time, often used in transportation studies to record vehicle velocity continuously. Mechanical tachygraphs linked wheel rotation to chart recorders, producing speed time curves. They helped analyze driving behavior, braking patterns, and compliance with speed limits. Modern digital loggers replaced them, but tachygraphs show how motion data once required dedicated mechanical recording systems. The odograph records cumulative distance traveled, typically using wheel rotations translated into mechanical counters or charts. Unlike simple odometers, some odographs produced continuous records showing when and how distance accumulated. Their role in surveying and transportation highlights the value of integrated measurement distance as a function of time rather than a final total. They remind us that movement history can be as informative as endpoints. The poviometer with chart recorder extends basic rain measurement by capturing rainfall accumulation over time on paper charts. This allowed hydrologists to see not just how much rain fell, but when it fell, and how intensity varied. Such records were crucial for flood analysis and watershed studies. Even as electronic sensors took over, these instruments demonstrate how slow environmental processes benefit from continuous, long-term observation. The sunshine duration recorder complements total solar radiation measurements by tracking when sunlight exceeds a brightness threshold. Mechanical versions relied on thermal or optical effects to mark exposure over time. They highlight how presence can be as important as quantity in environmental data. These instruments show how thresholds help simplify complex continuous phenomena into interpretable records. The thermohygrograph combines temperature and humidity recording in a single instrument, typically using bimetallic strips and hair elements linked to Penn's copa on a rotating drum. This allowed simultaneous tracking of two related environmental variables. Its decline followed the rise of digital multi-sensor loggers, but thermohygrographs illustrate early data integration. They show how correlated variables were once captured together mechanically, revealing daily and seasonal patterns. The barograph records atmospheric pressure, continuously using aneroid capsules linked to a Penn mechanism. Pressure changes over hours and days appear as smooth curves on chart paper. These records helped identify weather systems and forecast changes before satellite data existed. Barographs remain a classic example of slow change measurement, where trends matter more than instantaneous values. The microbarograph is a sensitive version of the barograph designed to detect very small pressure variations, such as atmospheric waves or distant explosions. It amplifies subtle changes that standard barometers might miss. Its applications include meteorology and geophysics. The instrument shows how refining sensitivity opens new observational windows, even for familiar variables like air pressure. The tilt meter measures very small changes in ground inclination over long periods. Early mechanical tilt meters used pendulums or fluid levels to detect gradual deformation. They are important in studying volcanoes, landslides, and structural stability. Tilt meters highlight how slow, nearly imperceptible motion can signal significant underlying processes. The creep tester measures slow deformation of materials under constant load over extended time. By recording strain over hours or months, it reveals time-dependent material behavior. These tests are essential for understanding long-term structural performance. The instruments emphasize that some properties only emerge when patience is built into measurement. The dilatometer measures changes in length or volume due to temperature variation. Early designs used mechanical amplification to detect expansion in solids and liquids. They helped establish thermal expansion coefficients and material compatibility. Dilatometers remind us that even rigid materials are quietly in motion when conditions change. The sedimentation balance measures how particles settle out of suspension over time, often used in soil science and chemistry. Changes in mass distribution are tracked as particles sink. This instrument captures slow processes governed by gravity and fluid resistance. It illustrates how time-resolved measurement can reveal particle size and interaction indirectly. The aging oven with recorder studies material degradation by maintaining elevated temperatures while tracking changes over long durations. Mechanical or chart-based sensors recorded conditions continuously. Such systems show how durability testing relies on sustained, controlled environments. They emphasize that understanding change often requires letting instruments run quietly for long stretches, faithfully documenting gradual transformation. The hour-angle sundial is a timekeeping instrument designed so that its shadow advances at a constant angular rate, matching Earth's rotation rather than the apparent seasonal motion of the Sun. By aligning the gnomon parallel to Earth's axis, the dial's hour lines become evenly spaced, allowing time to be read with surprising consistency throughout the year. This design transformed sundials from approximate seasonal indicators into instruments that reflected the deeper geometry of planetary motion. Its gradual disappearance came not from inaccuracy, but from convenience. Mechanical clocks freed timekeeping from weather, latitude, and careful alignment. Still, the hour-angle sundial remains a quiet demonstration of how astronomical understanding can be built directly into physical form, letting stone, metal, and sunlight cooperate to express rotational time. The equinoctial ring dial is a portable astronomical timepiece composed of a ring aligned with Earth's equatorial plane. When properly oriented, sunlight passes through a small aperture and strikes the inner surface of the ring, marking the hour scale engraved inside. Because the scale lies in the plane of Earth's rotation, the time markings are uniform, and the device works across seasons with minimal adjustment. Although compact and elegant, its accuracy depends on careful alignment and clear sunlight, limiting its everyday practicality. As watches became widespread, equinoctial ring dials became objects of study rather than use. Yet they remain a gentle reminder that time can be carried not only by springs or crystals, but by geometry carefully folded into metal. The armillary sphere is a skeletal model of the sky built from interlocking rings that represent celestial circles such as the equator, ecliptic, and meridians. While often displayed as an educational object, many armillary spheres were functional instruments, allowing users to visualize and calculate celestial bar, coordinates, rising and setting times, and angular relationships through physical rotation. Their role diminished as star charts, mathematical tables, and eventually software replaced hands-on celestial modeling. Still, armillary spheres embody a contemplative measurement philosophy. Understanding emerges through slow manipulation, where movement and alignment reveal relationships that numbers alone might obscure. The orrery is a mechanical model of the solar system that displays the relative motions of planets around the Sun. Driven by gears and cranks, it translates astronomical periods into visible cycles, allowing observers to follow conjunctions, oppositions, and orbital rhythms through steady motion. Though never perfectly accurate in scale or timing, orreries served as predictive and explanatory instruments. Their quiet value lies in showing that dynamic systems can be understood through analog motion, where gears carry knowledge forward turn by turn long before simulation became digital. The tellurian is a specialized astronomical model that demonstrates the relationship between Earth's rotation, axial tilt, and orbit around the Sun. By coordinating multiple motions, it illustrates seasons, day-night cycles, and eclipses through synchronized mechanical movement. Its educational clarity made it valuable in teaching, even if it was rarely used for precise calculation. The tellurian reminds us that some instruments are designed not to measure directly, but to make complex cycles feel intelligible through slow, coordinated motion. The pernisphere is a rotating star chart that shows which constellations are visible at a given date and time. By aligning date and hour scales, users can reveal the portion of the sky above the horizon, turning celestial mechanics into a simple manual adjustment. Although smartphone apps have replaced planispheres for most users, the instrument's enduring value lies in its simplicity. It transforms astronomical time into something that can be held, rotated, and quietly explored without electronics or computation. The Nocturnal is a nighttime timekeeping instrument that determines local time from the position of stars around Polaris. By aligning the device with the pole star and referencing specific constellations, users could estimate time without sunlight. Its use required familiarity with the night sky and clear viewing conditions, which limited its accuracy and convenience. Still, the Nocturnal reflects a period when time was read from the heavens directly, guided by patient observation rather than ticking mechanisms. The Meridian telescope, fixed to observe only the north-south line of the sky, was used to measure precise transit times of stars. By recording the exact moment a star crossed the meridian, astronomers could refine star catalogues, determine local time, and support navigation. As movable telescopes and space-based astrometry advanced, fixed meridian instruments became less common. Yet they highlight how restricting motion can increase precision, allowing stability and repetition to take precedence over flexibility. The transit instrument is a form of telescope designed to rotate only in the plane of the meridian, supporting highly accurate timing and positional measurements. Its observations linked celestial motion directly to clock readings, forming the backbone of observatory timekeeping. Though largely replaced by automated systems, transit instruments emphasize how astronomy once revolved around disciplined routine, observing the same bee. Crossings night after night to build reliability through repetition. The zenith sector measures small deviations in latitude by observing stars passing close to the zenith. Its long focal length and careful leveling allowed detection of subtle shifts caused by Earth's shape and motion. These instruments helped reveal that latitude is not perfectly fixed, contributing to geodesy and Earth science. They remind us that even seemingly stable reference points drift slowly over time. The static magnetometer measures magnetic field variations while minimizing the influence of Earth's main field. By using paired magnets arranged to cancel dominant effects, the instrument becomes sensitive to small changes. Such designs were crucial in early geomagnetic research. Though modern sensors are more compact, static magnetometers show how clever symmetry can amplify sensitivity without electronics. The declination magnetometer records changes in the direction of Earth's magnetic field over time. By tracking the angular position of a suspended magnet, slow geomagnetic variations could be observed and logged. These records helped establish geomagnetism as a dynamic system. The instrument underscores the value of long-term observation, where gradual shifts carry scientific meaning. The magnetograph continuously records magnetic field variations using mechanical linkages and chart recorders. It transformed invisible magnetic changes into time-based traces. Although digital magnetometers now dominate, magnetographs illustrate how Earth's magnetic behavior was first understood through slow, faithful recording. The torsion balance measures extremely small forces by observing the twist of a fine fiber. Its sensitivity allowed investigation of gravitational, electric, and magnetic forces at scales otherwise inaccessible. From fundamental physics to material studies, torsion balances demonstrated that delicate equilibrium could reveal profound truths. They remain symbols of patience and precision in measurement. The Cavendish balance is a specific torsion balance used to measure the gravitational constant. By observing minute attractions between masses, it quantified gravity itself in laboratory form. Its legacy lies not only in the value measured, but in proving that even universal forces can be weighed, given enough sensitivity and calm observation. The electrometer detects and measures electric charge or potential using mechanical deflection. Early designs used gold leaves or fibers that moved in response to electrical forces. Though replaced by electronic voltmeters, electrometers show how electricity was once sensed visually, turning invisible charge into motion. The gold leaf electroscope indicates the presence and relative magnitude of electric charge by leaf divergence. It offered immediate visual feedback without numerical readout. Its simplicity made it a staple of early electrical experiments. The instrument reminds us that detection often precedes quantification in scientific progress. The cloud chamber visualizes the paths of charged particles through supersaturated vapor. As particles pass, they leave trails of condensed droplets, revealing motion otherwise unseen. Though replaced by advanced detectors, cloud chambers transformed particle physics by making the invisible visible, turning fleeting events into observable power. Tracks. The bubble chamber operates on a similar principle, using superheated liquid to reveal particle paths as strings of bubbles. It provided clearer, denser records of high-energy interactions. Its decline came with electronic detectors, but the chamber remains iconic, showing how careful preparation of matter can make fundamental processes gently reveal themselves. The photographic emulsion detector records particle interactions directly in layered film. Tracks appear after development, frozen permanently in the material. Though slow and labor-intensive, these emulsions captured discoveries that shaped modern physics. They illustrate how patience and careful analysis can extract meaning from quiet traces. As these instruments fade from everyday use, they leave behind a shared lesson. Measurement is not only about speed or automation, but about attention, alignment, and time. Many of these devices ask the observer to wait, to repeat, and to trust slow accumulation over instant result. In their stillness, they remind us that understanding often arrives not with noise or urgency, but gradually, through careful watching and gentle persistence.